Hi everyone, good morning. So shall we start? In this lecture, we will study coloring. Two type of coloring we will study, vertex coloring and edge coloring. Okay, what is this concept of coloring? So let's start with this. So first we will start with vertex coloring. What is the concept of vertex coloring? So you can notice that, see, the definition is very simple. We just have to apply the definition. So please read the definition. Give neighbor vertices different colors. This is the concept of vertex coloring. So we want to color the vertices. To every vertex, we want to give a color. But remember, what should happen? That neighbor vertices, adjacent vertices, they should get different colors. So this is the definition. So let's see the definition of vertex coloring. Vertex coloring, the definition is very simple, that a graph coloring, or I can say vertex coloring, by default, let me tell you, there are two types of coloring. Yes or no? One is vertex coloring, another is edge coloring. Okay. So first we will study vertex coloring. And by default, when I say graph coloring, or by default, when I say coloring, then what it means? It means vertex coloring. It does not mean edge coloring. It means vertex coloring. So by default, coloring means vertex coloring. By default, graph coloring means vertex coloring. Okay. So first we will study vertex coloring, and then we will study this edge coloring. So let's see the concept of vertex coloring, or I can say graph coloring. What is that? This is basically, you are assigning colors. Okay, you are assigning colors to the vertices, such that to the vertices we want to give colors such that no two adjacent vertices share the same color. See, read this. No two adjacent vertices. Okay, so no two adjacent vertices, they have the same color. This is the definition. So just focus on the definitions, read the definition, and this is your concept. We have to analyze this concept now. Okay, so the concept is actually very simple. So for example, if you have a graph, like for example, if you have this graph, okay, now what we want to do, we want to do vertex coloring, means the adjacent vertices, they should get different colors. For example, here these vertices are adjacent, so they should get different colors. These two, can they get same color? Can they get same color? These two, can they get same color? Yes. Okay, we don't care about them. They can get same color or different color. We don't care about them. Okay, we don't care about them. So is this clear? See, we only care about adjacent vertices. Adjacent vertices, they should get different colors. For example, if I give red color to this, then I should not give red color. Okay, because they are adjacent. So adjacent vertices should get different colors. If I give red color here, green color here. But remember, I don't care about non-adjacent vertices. For example, this vertex and this vertex, they are non-adjacent. They are non-adjacent. So if I give red color here, I can give red color here, or I can give green color here. That is my choice, like whatever I want to do. Okay. So this is the idea. Graph coloring means, read the definition. Graph coloring means no two adjacent vertices should get same color. We only care about adjacent vertices. We don't care about non-adjacent vertices. So if two vertices are non-adjacent, like okay, like this vertex and this vertex, these two vertices are non-adjacent, so I can say they, okay, we don't care about them. They can get same color or they can get different color. We don't care about them. But the adjacent vertices, they should get different colors. They should get different colors. So you can notice this is a graph coloring. In this diagram, can you notice in this diagram that the you can notice the adjacent vertices, they have different colors. For example, these two vertices are adjacent, they have different colors. These two vertices adjacent, they have different colors. See, they are not adjacent, so they can have same color. They can have, for example, these two are also not adjacent, these two, so they can have same color, different color. We don't care. Okay, but remember, if you have adjacent vertices, they should get different colors. You can notice adjacent vertices, they have different colors. These two are adjacent, they have different colors. These two are adjacent, they have different colors. So is the definition clear? Let me know. Let's see this example. For example, this graph is this graph same. These two graphs are same basically. Okay. Now you can notice here that adjacent vertices, they have different colors. Yes or no? For example, these two vertices are adjacent. Notice that these two vertices are adjacent and they have different colors. These two vertices adjacent, they have different colors. They have different colors. Okay, so adjacent vertices should get different colors. This is the definition. Is the definition clear to everyone? What is a coloring? Coloring means color the vertices. To the vertices, we want to give the color such that no two adjacent vertices should get same color. This is called coloring, or you can call it proper color. Okay, so both are same. You can call it proper coloring or you can call it coloring. So both are same. So what is the idea? Color the vertices such that no two adjacent vertices, they get the same color. For example, here, tell me one thing. If I give red color to this vertex, tell me one thing. If I give red color to this vertex, if I give red color to this vertex, can I use this red color here? Can I use this red color here? No, because they are adjacent. Okay. Remember, adjacent vertices should get different colors. Adjacent vertices should get different colors. So I need to give some different color. Okay. Now tell me, can I give this yellow color here? Can I give this yellow color here? No. Okay. So can I use this red color here? No, because they are adjacent. Adjacent vertices should get different colors. So finally, what I can do, I can give basically, I can give this color. I can. Okay. So for example, I can give this color. Okay. So this is the idea. So, okay, idea is very simple that adjacent vertices should get different colors. Okay. This is the definition of coloring, or you can say vertex coloring, or I can say, so by default, you can call it coloring. You can only call it coloring, or you can call it vertex coloring, because I told you by default coloring means vertex coloring. By default, okay, you can call it graph coloring, because I told you that by default graph coloring means vertex coloring. Okay. And so this is the idea: coloring, vertex coloring, or I can call it proper vertex coloring. Another name is proper vertex coloring, or I can say proper coloring. I can say proper coloring. Okay. Proper coloring, proper vertex coloring. So what this means? This simply means that every pair of adjacent vertices, if two vertices are adjacent, okay, every pair of adjacent vertices should get different color. Okay, must get different colors, different color or label. Different, either you can call it color or you can call it label. So they must get different colors. Okay. So for example, here, this graph is same as this graph. These two graphs are basically same. They are isomorphic to each other. Okay. These two graphs are isomorphic. So let's see here. Is this proper coloring on your screen? Look at this. Is this proper coloring? Tell me, is this proper coloring? Look at your screen. So, and tell me, is this proper coloring? Yes, this is proper coloring, right? Okay. So this is proper coloring because you can notice that adjacent vertices have different colors. Okay, no two adjacent vertices, they have same color. Can you notice? Okay, Akash, no two vertices have same color. Adjacent vertices have different color. So that's the simple idea. So now let's see the next concept. Okay, tell me one thing. Tell me one thing. If I give you this graph like A, B, C, D, and if I ask you to color this graph, what is the most trivial thing? If I ask you to proper color this graph, what is the most trivial without using your brain? What is the most trivial solution you will give? Most trivial solution you will give. Four colors. Yes. What you will say? You will say to every vertex give different color. Okay. Why bother? Right. Okay. Very trivial solution. What will be the trivial solution? Like what will be a trivial solution? So the trivial coloring, I can say. What is a trivial coloring? You can simply say that to every vertex you give different color. Okay, every vertex different color. Every vertex different color. Hi all, am I audible? Hi everyone. Okay, so let's start now. So what I'm saying, this is the trivial solution. This is the trivial coloring. What you can do, every vertex you can give different color. So for example, color number 1, color number 2, color number 3, color number 4. Okay, this is the trivial solution. Now you can notice, because every vertex have different color, so I can say that adjacent vertices, they don't have same color. You can notice adjacent vertices, like they are adjacent vertices, they have different color. Adjacent vertices have different color. This is the trivial coloring. So I can say that this graph is 4 colorable. So I can say this graph is 4 colorable because you can color it using 4 colors. Can I say this is 4 colorable? 4 colorable. Can you color it using 4 colors? Yes. Yes, you can color it using at most 4 colors. This basically means at most 4 colors you will need. Okay, so this is 4 colorable. Now let's see this same graph. Is it 3 colorable? This same graph, is it 3 colorable? Is this graph 3 colorable? Can you give a 3 coloring for this? Is this graph 3 colorable? Can I color this using 3 colors? Yes. What I can do, I can give color number 1 here, or maybe color number red here. Okay. Now I cannot give color number red here. I have to give color number green here. Then what I can do, I can do color number blue here, and I can do green color number red here. Okay. So this is the idea. So is this 3 colorable? Yes. Is this graph 3 colorable? 3 colorable, because using 3 colors you can do it. Okay. So this graph is 3 colorable also. Okay. Remember what K colorable means. What K colorable, whenever we say K colorable, what that means. K colorable means, it means using at most K colors you can do it. Okay. K colorable, it means you can color it using K colors. It means basically using at most K colors. Using at most K colors. At most K colors. Okay. Using at most K colors you can color it. Okay, we can color. This is the definition of, okay. So you can notice, see, can I give this red? Can I give this color red? Like red here, can I give this? Yes, because they are non-adjacent. We don't care about non-adjacent vertices. We only care about adjacent vertices. Adjacent vertices should get different color. Adjacent vertices, they get different color. We don't care about non-adjacent vertices. The non-adjacent vertices we don't care about. But adjacent vertices, they must get different color. So what is the definition of K colorable? K colorable means using at most K colors. Using at most K colors, can you color it? Tell me, is this graph 1 colorable? Is this graph 1 colorable? This graph. Is this graph 1 colorable? Like, can I color this graph using 1 color? Is this graph 1 colorable? So the answer is no. Just think about it. If I give same color to everyone, 1 colorable means you can use only 1 color. So this graph is definitely not 1 colorable. So this is not a coloring. This is not a proper coloring. This is not a proper coloring. Or I can say this is not a coloring. So I can simply say that this is not correct. Okay. This is not a coloring. This is not a proper coloring. Because you can notice adjacent vertices, they have same color. These two adjacent vertices, they have same color. So I can say, is this one colorable? The answer is no. Now, is this 2 colorable? Is this graph 2 colorable? Can I color this graph using 2 colors only? At most 2 colors. Yes, because what you can do, see, if I use red color here, okay, if I use red color here, now I cannot use red color here and here. I cannot use. So let me use yellow color here, yellow color here. See, let me use yellow color here. Now I can reuse color yellow here because they are, okay, there is no problem. I can reuse because you can notice this is red. So they have adjacent vertices, they have different color. And here also what I can do, I cannot use yellow color. I cannot use yellow color, but I can use red color. So this is the idea. Okay, so is this 2 colorable? Yes. Can you notice for this graph, what is the minimum number of colors required? For this graph, what is the minimum number of colors required? Like if I ask you minimum number of colors, what is that? Minimum number of colors needed. That is 2. 2 is the minimum number of colors needed. So I can say this is chromatic number. This is your chromatic number, means minimum number of colors needed. This is called chromatic number. This is known as chromatic number. Chromatic number means what is minimum number of colors needed. Minimum. How many minimum colors you need, that is the chromatic number. Is this clear, the definition? So let's see the definition of K coloring. K coloring means at most K colors you will use. Okay, so this is the idea. K coloring, that simply means at using at most K colors, can you do it? Using at most K colors, can you do it? Okay, so what is K colorable? K colorable means at most using, okay, at most K colors. Can you color using at most K colors? Okay, so this is the idea. But for example, this graph, tell me, can I say this graph is 6 colorable? Can I say this graph is 6 colorable? Look at this graph. Can I say this is 6 colorable? The answer is yes. Can I say this is 10 colorable? Can I say this is 10 colorable? Can I say this is 10 colorable? The answer is again yes. Array 10 K colorable means at most K colors. K colorable means can you do it using at most K colors? A graph is K colorable if you can do it using at most K colors. So using at most 10 colors, can you do it? Yes. Is this clear? See, K coloring, look at this, K coloring, K coloring. K coloring means using at most K colors, can you do it? Using at most K colors, can you do it? Like using at most 2 colors, can you do it? Using at most 1 color, can you do it? So is this 10 colorable? Yes. Is this 100 colorable? Using at most 100 colors. At most 100 colors you can use. At most 100 colors you can use. Is this 100 colorable? Yes. Okay. Tell me one more thing. Let's see. Is this 5? Is this a 5 colorable? Okay. So this is 6 colorable. This is trivial, right? This is trivial. 6 colorable is trivial because you can give different colors to every vertex. Okay. To every vertex you can give different. Let's see this 5 colorable. Is this 5 colorable? Can you do it using at most 5 colors? Okay, let's see. Can you do it using at most 5 colors? This is what we have to check. So let's see what, okay, tell me one thing. You tell me one thing. If I give color number 1 here, if I give color number 1 here, can I give this color number 1 here? No, because they are adjacent. So I have to give color number 2 here. Can I reuse color number 1 or 2 here? Can I reuse color number 1 or 2 here? Can I reuse? Okay, I cannot reuse. I cannot reuse. So I need color number 3 here. I cannot reuse because they are, this is a triangle. This is a cycle. Okay, so they are adjacent to each other. Okay, can I reuse any of these color? Can I reuse any of these color? Can I reuse? Can I reuse? No, I cannot reuse. So I need another color. Okay, I need another color. Now, so I can give color number 5 here and I can give, can I reuse color number 2? Can I reuse color number 2? Yes. So this is 5 colorable. Yes, this is 5 colorable. So this graph is 5 colorable. Is this graph 4 colorable? Is this graph 4 colorable? Can we color this graph using 4 colors? So let's see. So you can notice one thing. If I give color number 1 here, I cannot give color number 1 here. So let me give color number 2. For this vertex, I cannot reuse these 2 colors. So let me give color number 3. Now these 3 colors I cannot use for this vertex. So let me give color number 4. Now, is this 4 colorable? Like, can I reuse? For example, can I reuse color number 1? Yes, I can reuse. Can I reuse color number 2? Yes, I can reuse. So is it 4 colorable? Yes, this is 4 colorable. Is this graph 3 colorable? Is this graph 3 colorable? This graph. Can you color it using 3 colors? Okay. Can you color it using 3 color at most 3 colors? At most 3 colors you can use. Okay, at most 3 colors you can use. You cannot do it. Just check it. Just look at this area. Just look at this area. This is a K4. Can you look at this area? This is a K4. Every vertex is adjacent to another vertex. Can you color this graph using 3 colors? At most 3 colors. At most. Okay, just notice one thing. If I give color number 1 here, I cannot reuse this color in this area. In this area, I cannot reuse because they are adjacent. because they are adjacent. So I cannot reuse this color. Okay, so here I have to give color number 2. I cannot reuse this color number 2 in this area because this is complete graph on 4 vertices. Every 2 vertices are adjacent. I cannot reuse. I cannot reuse. I cannot reuse because you can notice they are adjacent. So I have to give different colors to every vertex. So minimum 4 colors I need. So is this 3 colorable? The answer is no. This is not 3 colorable. I can say minimum 4 colors you need. Minimum. Okay, so tell me minimum how many colors you can do. So this is 4 colorable and this is the minimum number, right? This 4, if you notice, this is the minimum number of colors needed. This 4 is the minimum number of colors needed. Colors needed. Okay, so this 4 is basically the called chromatic number. So this 4 is called chromatic number. Chromatic number means minimum how many colors you need. So this 4 is your chromatic number. So what is chromatic number? Chromatic number is 4 and the symbol is zeta, whatever. Okay, so this is the symbol. This is the symbol. So what is the name of this symbol? So let me tell you that the name of this symbol is zeta. And this is your, so I can say this is the idea. And the name is zeta. Zeta. Okay, zeta, whatever. Like this. So zeta of G. This is the chromatic number, remember. So what is chromatic number? That is minimum number of colors. How many minimum number of colors you need? That is the chromatic number. So for this graph, chromatic number is 4 because you can do it using 4 colors and you cannot do it using 3 colors. Okay, is this clear to everyone? So what is a trivial solution? You know, trivial solution means give different color to every vertex. What is a chromatic number? So what is the interesting problem? This is not an interesting problem. If I ask you maximum how many colors you need, that is not interesting, right? But if I ask you minimum how many colors you need, minimum possible. If I ask you how many minimum possible colors you need, so that is interesting problem. And this is called chromatic number. This is known as chromatic number. For example, in this graph, can I say this is 3 colorable? This graph, is it 3 colorable? Yes, this is 3 colorable. You can notice green, red, blue. So this is 3 colorable. But what is the chromatic number? Minimum how many colors you need? Minimum 2 colors you need. You can notice. Can I do it using 1 color? Can I do this graph using 1 color? No, I cannot use. Okay, I cannot use 1 color. Okay, so the chromatic number will be 2. Minimum 2 colors you need. So this is the idea. But remember this graph, I can say this graph is 3 colorable. I can say this graph is a 3 colorable because at most 3 colors you need. This graph is 3 colorable. And the chromatic number is minimum these many color you need. So what is the chromatic number of a graph? Chromatic number of a graph, that means what is the minimum possible number? Minimum possible number of colors that you need. Okay, so this is the symbol is zeta of G. Now let's see. So yeah, we have seen the definition of chromatic number, and this is very important concept. Chromatic number means minimum number of colors needed. Minimum how many colors you can use. Okay, so that is the idea. Remember K coloring. What is the K colorable? K colorable means at most K colors. K colorable simply means at most K colors. And the smallest value of K, that is your chromatic number. Let's move on. So okay, so this graph we have already seen, and you can notice that this is 4 colorable. So for this graph, the chromatic number will be 4. You can notice. Okay, so this is the idea. Now let's see one by one for many different graphs. So remember, if a graph is K colorable, what that means? K colorable means if you can color using at most K colors. This is the K colorable. And minimum number of colors that you need, that is your chromatic number. This is the minimum number of colors you need. Now let's see. First we will see for complete graph. What can you say about complete graph? One by one, let's see every graph. What is the chromatic number? Remember, chromatic number is interesting problem. So let's see the chromatic number of complete graph. What will happen to the complete graph? If your graph is complete graph means Kn. Kn means complete graph on n vertices. Okay, so this is your complete graph on n vertices where every 2 vertices are adjacent. So this is a complete graph on n vertices. So there are total n vertices and every 2 vertices are adjacent. So how many colors? What is the chromatic number? What do you think? Minimum how many colors you need? What is the chromatic number of Kn? The chromatic number of Kn will be, tell me one thing, can you reuse in this Kn, can you reuse a color? Can you reuse a color? You cannot reuse a color. Okay, so that is the reason chromatic number will be n, because notice you cannot reuse. If I give you, for example, if I give you this graph, this is your K1, and the chromatic number here is chromatic number for this graph, that is 1. Okay, because you can give red color here, you can give red color here, so this chromatic number is 1. Next, if I have this graph is K2, and here the chromatic number will be what? That will be, because you cannot reuse. If I give red color here, I cannot give red color here, I cannot give, so you cannot reuse the colors. Okay, next, for example, this is your K3, this graph is K3. Hi everyone, is there any disturbance in the audio video? Let me know. Is it smooth? Disturbance in the audio. So, okay. Is it clear now? Okay. So let's see. Okay. Yeah. So this is your K3. You cannot reuse a color. You can notice if I give red color here, I cannot give red color here because every two vertices are adjacent. Okay. You cannot reuse a color. If I give red color here, you cannot give red color here. You cannot give red color here. So that is the idea. I have to give different colors. I have to give. So for this graph, the zeta will be 3. So this is the simple idea that if you have a complete graph, okay, like you have these vertices, okay, let's assume these vertices you have like 1 2 3, okay, these vertices like a1 a2 a3 and so on, like a1 a2 a3 and so on, an. So these are your vertices. Now for these vertices, you can notice that you cannot reuse a color. This is the thing you should notice, that you cannot reuse a color. Okay, in kn we cannot reuse a color. We cannot reuse a color because every two vertices are adjacent, so we cannot reuse a color. If you reuse a color, then what will be the problem? Just think about it. We cannot reuse a color. Why? Because if you reuse a color, let us assume you reuse like this. Okay, let us assume you reuse like this, red here, red here. Okay, if you reuse, then what is the problem? What is the problem? Because this is a complete graph, so every two vertices are adjacent. Every two vertices are adjacent, so you cannot reuse a color. So that is the reason every vertex should get different color. Okay, so the chromatic number for complete graph, that will be n. So if you see a complete graph in your life, okay, whenever you see a complete graph, then immediately you know that if you have a complete graph on n vertices, definitely n colors is definitely needed whenever you see a complete graph. Let's see the next graph, that is ageless graph, en. This is your favorite ageless graph. Okay, so you have ageless graph. This is the ageless graph on n vertices. So here, what will happen for this graph? What is the chromatic number? So only one color is enough because here there is no age. So there are no adjacent vertices. So the only one color is needed. Okay, so I can say the chromatic number will be 1. Minimum only one color is needed. To every vertex, you can give same color. Okay, so for example, if you have E4, then this is your E4, A, B, C, D. This is the E4. Then what you can do? You can give same color to the every vertex. You can give same color to every vertex. Very simple. To every vertex, you can give same color you can give. So this is the ageless graph. Now let's see the next graph, that is path graph. What will happen to the path graph? Pn. What will happen to the path graph on n vertices? For example, if you have P3, then what will be zeta? If you have P3, then what will be the chromatic number? What you can do, minimum how many colors? See, very simple. If you give color number 1 here, you can give color number 2 here, you can reuse. Again, you can reuse, right? So, okay, so very simple. See, if I give color number 1 here, I cannot give color number 1 here. So let me give color number 2. I can reuse the color number 1 again. So here the zeta will be 2. Okay, if you have P2, then also zeta will be 2. If you have P3, sorry, P4, if you have P4, then also zeta will be 2. Then also chromatic number will be 2, because you can give color number 1 here. You cannot give color number 1, but again you can reuse. And again you can reuse color number 2. You can reuse. Okay, so very simple. So the zeta will be 2. So any graph you take, if you have any Pn, then what will be the chromatic number? Minimum 2 colors is enough. So this is the chromatic number. Is this clear? Only 2 colors are enough. You can reuse. I am asking chromatic number. Chromatic number means minimum how many colors you need. I am asking chromatic number. I am asking chromatic number. Chromatic number means minimum how many colors you need. Minimum colors needed. So whatever graph you, okay, so that is the reason. But remember, for P1, what will happen? For P1, if you have this graph P1, for P1 the chromatic number will be 1. For P1 the chromatic number will be 1. So here when n is greater than equal to 2, then chromatic number will be 2. Is it clear to everyone? Let me know. Let's see the next category of graph. The next category is, so this is 3 and this is 4. The next category is cycle graph. What about cycle graph? So you can notice this is your C3, this is your C4, this is your C5, this is your C6. So tell me what I can do for cycle graph. This is C3. So I need chromatic number is 3. Okay, because this is a complete graph. So every vertex should get different color. And here you can, what you can do in C4, what you can do, I can give color number 1 here. I cannot reuse color number 1 here. So let me give color number 2. Can I reuse color number 1 here? Yes. Okay, so can I reuse color number 2 here? Yes. So for C4 the chromatic number will be 2, and for C5 the chromatic number will be again 3, because if I give color number 1 here, I cannot give color number 1 here. So I can give color number 2. I can reuse color number 1. I can reuse color number 2. But notice, I cannot reuse color number 2. I cannot reuse color number 1. So I have to give color number 3. Okay, and what about this C6? This C6, for this chromatic number will be 2, because what you can do, color number 1, color number 2, 1, 2, 1, 2. Okay, so this is the idea. For for a cycle graph, what will happen? For a cycle graph, the answer will be 2 when n is even. When n is even. Okay, so the chromatic number will be 2. I can say the chromatic number will be 2 when n is even, and the chromatic number will be 3 when n is odd. So this is very simple. Let's see the next category of the graph. That is the bipartite graph. What do you think about bipartite? What do you think? What is the bipartite graph chromatic number? Some students are saying 2. Some students are saying 2. Tell me, is this bipartite graph? Is this bipartite graph E3? Is this bipartite graph? Some students are saying 2. Is this bipartite graph? This is not bipartite. This is a bipartite graph. Yes, this is a bipartite graph. And this is bipartite, right? Bipartite means you can create 2 partition. Yes, I can create 2 partition A, B, C. I can create 2 partition C. I can create 2 partition. And you can notice there is no A's here. You can notice there is no A's here. So this is correct. There is no problem. So this is a bipartite graph. We have already seen in the bipartite graph. I told you bipartite means there is no odd cycle. A graph is bipartite if and only if there is no odd cycle. A graph is bipartite if and only if, just use this. A graph is bipartite if and only if there is no odd cycle. If and only if there is no odd cycle. So you can notice there is no odd cycle here. You don't have any odd cycle here. So this graph is bipartite. You can create two partition, you can create. And you can notice there is no edge here, there is no edge here. So this is a bipartite graph. What is the chromatic number for this bipartite graph? That is 1. Okay. So tell me, if I have this bipartite graph, for example, if I have this type of bipartite graph with at least one edge, with at least one edge, if I have a bipartite graph with at least one edge, with at least one edge, if I have, then what will be the chromatic number? If I have at least one edge, see, if I have at least one edge, then the chromatic number cannot be 1. Yes or no? The chromatic number cannot be 1. Now the chromatic number will be 2. Why the chromatic number will be 2? Because see, there is no edge here. These are non-adjacent. All these vertices are non-adjacent. So I can give same color to them. I can give color number red here. Okay, I can say this is the red class. I can say this is the red class, and I can say this is the blue class. Because these are also non-adjacent. So finally, I can say that these are non-adjacent, so I can give same color them, and these are non-adjacent, I can give same color to them. And you can notice that every edge will have different colors. Yes or no? Every edge will have different colors at their end point. So you can notice. Yes or no? So very simple, the chromatic number will be 2. I can say one thing, I can say for bipartite graph, what will be the chromatic number? If I directly ask you the bipartite graph, the chromatic number, the bipartite graph chromatic number, that will be less than equal to 2. Means I can say bipartite graphs are too colorable. Remember, bipartite graphs are too colorable. Bipartite graphs are too colorable because you need at most 2 colors, are too colorable. But chromatic number is what? The chromatic number is less than equal to 2. Okay, remember, too colorable. That simply means chromatic number is less than equal to 2. If a graph is k colorable, then what can you say about chromatic number? If you know G is k colorable, then what can you say about chromatic number? If you already know G is k colorable, then what can you say about chromatic number? Chromatic number means minimum how many colors you need. Minimum how many colors you need. You already know it is k colorable, so minimum you need minimum how many colors you need? I can say, sorry, at most k colors you need. Yes or no? So the chromatic number will be less. If you already know the graph is k colorable, it means chromatic number will be less than equal to k. Okay, so here you can notice bipartite graph is too colorable. It means chromatic number will be less than equal to 2. Bipartite graph with at least one edge. Okay, there are two type of bipartite graph. Okay, bipartite graph with no edge. So if you have bipartite graph with no edge, either your graph does not have any edge, means your graph is basically edgeless. Your graph is edgeless. So this is your graph En. So what will be the chromatic number? Then the chromatic number will be 1. And if your bipartite graph has at least one edge, only two cases are possible. Your bipartite graph with at least one edge. At least one edge. So if you have at least one edge, then you cannot use one color. If you have at least one edge, then you cannot use one color. So I can say the chromatic number will be 2 here. So that is the reason chromatic number is less than equal to 2. Is it clear to everyone? Anyone has any doubt in this? If any graph has at least one edge, then what can you say about this? If any graph, if G has at least one edge, if G has at least one edge, if G has at least one edge, then what can you say about chromatic number? What can you say about chromatic number? That will definitely be greater than equal to 2. Chromatic number will definitely be greater than equal to 2. If your graph has, I can say, this is the idea. So let's see. So we have seen the Kn, we have seen edgeless graph, we have seen bipartite graph, we have seen. So bipartite graph with at least one edge, they have chromatic number 2. Okay. So let me just connect to the internet. Hi everyone, audible? Am I audible? Okay, so let's see now the next category of the graph. What is the next category? So we have seen how many categories we have seen? 5 categories we have seen. Let's see the complete bipartite graph. The sixth category, the complete bipartite graph, KMN. Okay, so what can you say about KMN? Where m is also greater than equal to 1 and n is also greater than equal to 1. So let's assume m is greater than equal to 1, n is greater than equal to 1. For this, again, this is a bipartite graph. And if you have at least one edge, then the answer will be 2. If you have at least one edge, then the answer will be 2. So the chromatic number will be 2. But remember, again, if you don't have edge, again, for example, if you have KMN, where let's assume m equal to 0 or n equal to 0. Okay, means you have KMN where m equal to 0 or n equal to 0, then the chromatic number will be 1. Again, the same thing. So the chromatic number will be, okay, because this is a bipartite graph. You already know this is a bipartite graph. So that is the reason I can say like this. But if you have, for example, if your graph is like this is also complete bipartite graph. This graph is also complete bipartite. This is K3, 0. So for this graph, the chromatic number will be 1, only one color you need. Okay. And if you have at least one edge, means, okay, then the chromatic number will be 2. And what can you say about the question number 7? What can you say about QN? QN. What can you say about your hypercube graph? This is your hypercube graph on n vertices. So what can we say about this QN? Let me tell you one thing. Whenever I tell you about QN, what comes to your mind? What should come to your mind? Whenever I say QN, what should come to your mind? Bipartite. Remember? Okay. Most of the time, remember, most of the time, okay, we do analysis of Kn. Okay, we do analysis of Kn from bipartite point of view. We do analysis of Qn, okay, from bipartite point of view. From bipartite point of view. Because this is a bipartite graph. You already know this point of view. This is your favorite bipartite graph, this Qn. This is your favorite bipartite graph. Okay, in this bipartite graph, what we have? There is something called a odd parity, even parity. This concept we have already seen. All the odd parity vertices will be here. All the even parity vertices will be here. Okay, so all the odd parity, even parity vertices will be like this. So this is your bipartite graph. And because this is bipartite graph, so what will so tell me, what will be the chromatic number? The chromatic number will be 2 as long as n is greater than equal to 1. But if n is 0, like Q0, then the chromatic number will be 1. Because remember, Q0 means only single vertex. Q0 means a single vertex. Q1 means like this. This is Q1. And Q2 is like this. And Q3 is like this. Okay, so this is the idea. So you can notice, remember, this is a bipartite graph. You already know this. This is a bipartite graph. And if you have n is greater than equal to 1, then there will be at least one edge. Then the answer will be 2. And if n is equal to 0, then the answer will be 1. Okay, clear? All these points, are they clear? So did we leave any graph? Yes, wheel graph is there. Okay, so let's see the wheel graph. What can you say about wheel graph? Wn. How many vertices? This is a wheel graph on how many vertices? This is a wheel graph on n plus 1 vertices. So tell me, what is the chromatic number for wheel graph? For wheel graph. So you can notice, for wheel graph, you can think like this. See, there are two types of wheel graph. One is Wn, okay, which we get from odd cycle, where n is equal to odd. And one is Wn, where n is even, which we get from even cycle. So this Wn, where n is odd, this we get from odd cycle. It means there is an odd cycle around you. It means there is an odd cycle around you. There is an odd cycle. It means there is an odd cycle here. You have an odd cycle here, and there is a vertex here, and this vertex is adjacent to every other vertex. Tell me one thing, can you reuse this color? Can you reuse this color? This color can you reuse? Because this vertex is adjacent to every other vertex, you cannot reuse this color. This color we cannot reuse. Okay, so for example, let me give red color to this. Now I cannot reuse this color because this vertex is adjacent to every other vertex. And outside, what you have? Outside there is an odd cycle. And for this odd cycle, how many colors you need? For this odd cycle, how many colors you need? So for this odd cycle, you need 3 colors. For this odd cycle, you need 3 colors, and there is one color here. So finally, I can say that this will be chromatic number will be 4. Chromatic number will be 1 plus 3. I can say. Is this clear to everyone? Let me know. Because remember, you cannot reuse this color. Because if I give color number red here, then this vertex is adjacent to every other vertex. So I cannot reuse this color. And the odd cycle, we already know. For odd cycle, the chromatic number is 3. For this odd cycle, the chromatic number will be 3. And in this situation, what will happen? There is an even cycle. There is an even cycle. You already know. Okay, so this is your, I can say this is an even cycle. And there is a middle vertex. This middle vertex, you cannot reuse the color. If I give color number red here, and for even cycle, how many you need? Only 2 you need. So finally, here the answer will be chromatic number will be 1 plus 2. So the chromatic number will be 3. Okay, so finally I can say for Wn, what will be the chromatic number? The chromatic number will be 2. Chromatic number will be 3 when n is even. When n is even means when you have outer cycle, this outer cycle you have even. And if n is odd, then the chromatic number will be 4. For example, if you have W3, W3 is same as what? W3 is same as K4. You already know. So because W3 is K4, so how many colors you need? So that how many colors? Or 4 colors you need. Okay. So very simple. So this is your W3. Your W3 is actually like this. This is the W3. Now you can notice that this color I cannot reuse. Okay, if I give this color here, I cannot reuse this color. So for outer cycle, I need 3 colors, you know, because there is a odd cycle. Outer cycle is odd cycle. So I need 3 colors. Okay, and the middle color I cannot reuse. So that is the reason this when n is odd, so then you will need chromatic number equal to 4. And when n is even, then chromatic number will be 3. So all the graphs we have seen. The pentagon means cycle of length 5. The chromatic number will be 3. So for any odd cycle, the chromatic number is 3. Okay. So this graph, what is this graph? Can anyone tell me? This graph is your W. This is your wheel graph. This is W4, and for this chromatic number will be 3. You can check it out. The chromatic number is 3 because we cannot reuse this color. This middle color we cannot reuse. And outside you have a even cycle. Outside there is a even cycle. For even cycle you need 2 colors. Okay, this is chromatic number 2, and for this chromatic number will be 4 because this is your this is the idea. So remember, K vertex coloring means at most K colors you need. Okay, this is not K5. Is this K5? Arpan, this is not K5. K5 means every vertex is adjacent to every vertex. Are they adjacent? Are they adjacent? This and this, are they adjacent? They are not adjacent. These are not adjacent. So this is not K5. These 2 vertices are not adjacent. These 2 vertices are not adjacent. Okay. So anyway, this is the idea. So this is the idea of coloring. So remember, if you have this graph, then coloring means that adjacent vertices should get different colors. Tell me, if you have isolated vertices, we don't care. They can get same color, different color, but adjacent vertices should get different color. Okay, adjacent vertices should get different color. So this is the idea. Now, So let's take this greedy algorithm, then we will take a break, small break we will take. So but let's see what is this algorithm. Can you notice how you are coloring? If you observe how you are coloring, so what is the greedy method? Like what is the method we have seen so far for coloring? Procedure for coloring, the method, algorithm for coloring. Algorithm for coloring. What is the algorithm we have seen? Algorithm for coloring. This is the algorithm we have seen. We start at a vertex. Yes or no? For example, let me give you this graph. Let me give you this graph. A, B, C, D, E, okay, F. So let me give you this graph. Now see what you are doing. You are starting at some vertex. Yes or no? What you are doing? How to do color? For example, what you are doing like this. You are starting at a vertex. For example, let me start at this vertex. Okay, so you are giving color number 1. Then what you are doing? So you are starting at a vertex and you are giving color number 1. And then can you reuse this color? Can you reuse this color? No. Okay, then you will give color number 2. You cannot reuse, so you will give color number 2. Now, can you reuse this color here? Can you reuse a color here? Can you reuse? So if you notice, you are using the minimum value. See, you are starting from 1. Okay, you are starting from this vertex, you are giving value 1. To this vertex, you cannot give value 1, so you are giving value 2. Then again, what I will do? To this vertex, I will give value 2. Because this value is available now. Because they are not adjacent. So this value 2 I will give, yes or no. I can reuse the color. So the algorithm, if you notice, that is basically reuse the labels. Reuse the labels. Yes or no, agree? Reuse the labels. If you notice, basically what you are doing, you are using the minimum label available. Using minimum label available. Yes or no? Minimum label available. So which minimum label? For this vertex, which minimum label is available? You cannot use this 1, but you can use this 2. Are you getting this point? Let me know. This is how you do. This is how you do algorithm for coloring, right? So you reuse the colors. It simply means that you are using the minimum label that is available. Okay, for this vertex, what should I do for this vertex? Tell me. For this vertex, what should I do? I cannot use 1, I cannot use 3, so let me use 3. I cannot use 1, 2. For this vertex, what I will do? Minimum color, just use minimum color. Minimal label you need. Okay, so I can use 1. I can use 1. Very simple. I'm reusing the colors. I'm reusing the colors. For this vertex, what you will do? You cannot use 1. You cannot use 2. You cannot use 3. So you can use what? You can use 4. Okay. And for this vertex, what you can do? Then you can use 1. Okay. So this is the algorithm. If you notice, this is the algorithm, means automatic procedure. Algorithm means automatic procedure. So this is your automatic procedure algorithm. What you are doing? You are reusing the labels. Means you are using the minimum label that is available. Minimum label that is available, you are using. This is called greedy algorithm. This is called greedy algorithm. Yes, D, E are adjacent. So they are different color. They have different color. Preeti, they have different color. These are the colors. Preeti, these are the colors. These are the colors. Is anyone has any doubt? Let me know. So basically, this is the algorithm, automatic procedure. The automatic procedure, what it will do? It will use the minimum color available. Yes or no? Very simple. Basically, we are reusing the colors. So just use the minimum color available. Very simple. This is called, this algorithm is basically the greedy algorithm. If you notice, what you are greedy. Okay, you are greedy. You want to use minimum amount. You are very greedy. Okay, maybe you are confused, so you want to use the minimum amount. So this algorithm is called greedy algorithm. So what is this greedy algorithm? So if you notice this algorithm, so this is your greedy algorithm. This is your greedy. Why this is greedy? Why we call it greedy? This algorithm, why we call it greedy? Because you are greedy about the minimum color. Like you are very greedy, you are very lalchi or whatever. Okay. So basically, you don't want to spend your money. Okay. Kusal is saying, if we use C, then Kusal, that's the idea. We will come back to this point. Don't worry about it. I will come back to this point. I'm just telling you, okay, that this is how the algorithm will work. Algorithm will work like this. Yes or no? Algorithm does not know from where to start. Okay. So Arpan is saying from vertex B, we use 2. Then for vertex C, we can use 2 again. Yes, Arpan, we can do that. I will come back to this point. Did you understand this? I know what you are saying. I know. So did you understand this? Okay. Just give me a second. And you find what is the chromatic number. Like see, so I can say this graph is, can I say this graph is 4 colorable? So I can say this graph is 4 colorable. I can say this graph is 4 colorable. So this graph is 4 colorable. Now find the chromatic number. Find that. Means minimum how many colors you need. Okay. So remember, yeah. So what I'm saying, so remember, this is the algorithm. Algorithm is this. For this graph, this is the algorithm that you will do. So what is the greedy algorithm? This algorithm is greedy because you are very greedy about the color that you are using. You want to use the minimum color. So this is your greedy algorithm. This is the greedy algorithm for coloring. Algorithm for coloring. What you will do in this algorithm, what you will do? If I ask you automated procedure, what you will do? Okay, forget about the graph. Forget about the graph. If I ask you to, okay, give me automatic procedure for coloring, then what you will do? You will say that start at a vertex. You will say that start at any vertex V. This is what you will say. You will say start at any vertex V. Okay, then what you do? Give it color. Give it color number 1. So you start at vertex number, any vertex V, give color 1. Give label 1. Label means color. So give label 1. Then what you do? Then basically you, okay, then what you do? So then what you will do here? So first you will do this. Then what you will do? Basically go to next vertex. Okay, go to any next vertex. Any next vertex. Go to any next vertex. Any vertex you can give. Okay, go to any uncolored vertex. I can say go to any uncolored vertex. Okay, and then what you do? Give minimum color available. Give minimum value. Give minimum value which is available. Which is available. Give minimum value which is available. What do I mean by available? What is the meaning of available? How to check available? Give minimum value which is available. It means basically minimum value which is not given to its neighbors. Means minimum value which is not given to its neighbors. Minimum value that is not given to neighbors. Not given to its neighbors. Okay, so this is the idea. Very simple. The minimum value you use the minimum value which is not given to its neighbors. That minimum value you use. Okay, so this is your greedy algorithm. But let me tell you one thing you can notice. This greedy algorithm will not give you the chromatic number. What this will give you? This is a very important note. This greedy algorithm will not give you chromatic number. Greedy algorithm does not give chromatic number. What it gives, greedy algorithm does not guarantee chromatic number. Does not guarantee. This is very important. Greedy algorithm does not guarantee chromatic number. Does not guarantee chromatic number. So the chromatic number it does not guarantee. Okay, but remember, basically this says that your graph will be k colorable. Okay, this greedy algorithm basically says your graph will be k colorable. It can only say that your graph is k colorable. It can only say this. This it can say, but it does not guarantee minimum colors. For example, this is your graph. Like this graph we have seen. In this graph, what I have done. So what I have done for this graph, if you notice, for this graph, I have colored it. Okay, I have colored this graph using the greedy algorithm. But how many colors I got? But how many colors I got? I got 4 colors. Okay, but if you see, if you change the vertex that you select, or maybe okay, if you apply this, so let me take this graph. Let me take this graph again. Okay, so let's take this graph. A, B, C, D, okay, E, F, G, H. So let me take this graph. Now notice few very interesting things. For this graph, if I start from here, just think about it. If I apply this greedy algorithm I apply, and let's assume I start from this vertex F I start. So if I start from this vertex F, so let me give color number 1. So what I will do color number 1. Then let me go to color number, okay, then I will give color number 2. Okay, then for this vertex I will use the minimum color available. For this vertex I will use the minimum color available, that is 2. Then for this vertex I will use the minimum color available, that is 3. Then for this vertex I will use the minimum color available, that is 1. Then for this vertex I will use the minimum color available, that is 4. And then for this vertex I will use the minimum color available, that is 1. Yes or no? So if I apply the greedy algorithm, okay, in this order, if I apply the greedy algorithm, then answer will be what? In this order, if I apply the greedy algorithm, then the answer will be what? Then the answer will be basically that 4 colorable. So I told you that it only tells us that this is 4 colorable. Greedy algorithm only tell us that it is 4 colorable. It does not say it is minimum. Greedy algorithm does not say it is minimum. Greedy algorithm says it is 4 colorable. Now let's apply the greedy algorithm again. Okay, first you understand the greedy algorithm. Please understand the greedy algorithm. What this algorithm is saying, you start from any vertex. For example, let me start from this vertex. So let me give color number 1. Then I can go to any vertex of my choice. I can go to any vertex and use the minimum color available. What is the minimum color available? The minimum color available is this. I can go to any vertex now. What is the minimum color available? That is 2. Okay. Next, what is the minimum color available here? That is 2. Okay. Next, what is the minimum color available here? For this, what is the minimum color available? That is 2. Next, for this vertex, what is the minimum color available? For this vertex, that is 3. And then for this vertex, what is the minimum color available? That is a 3. So can you notice that if I apply this greedy algorithm in this order, if I apply this greedy algorithm, in this order, then what this greedy algorithm will tell me? Then this greedy algorithm will tell me that this is 3 colorable. The greedy algorithm will tell me that this is a 3 colorable. Okay, at this moment, can I guarantee chromatic number will be 3? At this moment, can I guarantee chromatic number will be 3? Why I can guarantee? Because see, this is a triangle. Array, see, this is a triangle. So three colors we need. Yes or no, Kusal? We need three colors. Whatever you do, you cannot do using less than three colors. See, this is a triangle, and because this is a triangle, so we definitely need three colors. So this greedy algorithm is saying that three colorable, and this triangle is saying that definitely three colors is needed. Definitely minimum three colors is needed. So now finally I can say chromatic number will be what? Okay, so for this graph, you can notice for this graph, the greedy algorithm will give you what answer? The greedy algorithm will give you what answer? The greedy algorithm can give you answer 4, or the greedy algorithm can give answer 3. Remember, the greedy algorithm will give you answer 4 or 3. So you can notice one thing, that you cannot use the greedy algorithm to find out chromatic number. Okay, so this simply means that answer will be 3 colorable, and this answer we will take. Okay, so we will consider this answer 3 colorable. And this cycle, if you notice this cycle, if you notice, this is your cycle. This is your cycle C3, or I can say triangle. This is a triangle, or I can say this is K3, or I can say this is K3. So how many colors you need for K3? 3 colors is definitely. So you need definitely you need these many colors. Okay, and this is saying that at most 3 colors you need. This is saying at most 3 colors you need, and this is saying at least 3 colors you need. So from these two, what I can say? From these two, what I can say? From these two, I can say chromatic number is 3. Is this clear to everyone? Let me know. So did you understand the greedy algorithm? Did you understand the greedy algorithm? So, okay, color a vertex with color number 1. So you start with a vertex, you give color number 1. Then you go to uncolored vertex. You go to uncolored vertex and you give the lowest number available. What you do? You will give the lowest number available. That is not given to its adjacent vertices. That is not given to its neighbors. Okay, so give a lowest color available that is not given to its neighbors. Okay, this is your greedy algorithm for vertex coloring. But remember this is very important point. It does not always succeed in finding the minimum number of colors. Okay, but at least this will give you proper coloring. It will tell you that you have K coloring. So okay, so this is very important point. Now let's see one more point. From this greedy algorithm, you make this observation. That, for example, let's assume you have a graph, and in this graph, let's assume that maximum degree means this is maximum degree. Let's assume maximum degree is a 4. Then what can you say about chromatic number? Like, you don't have any information about the graph, but the maximum degree is 4. For any vertex, the maximum degree is 4. Then what can you say about the chromatic number? What can you say about the chromatic number? What can you say about the chromatic number? If the maximum degree is 4, the chromatic number. See, very simple point. Okay, just apply the greedy algorithm. See, this means that what it means? It means there is some vertex. It means there is, okay, maximum degree is 4. So let's assume vertex A. Let's assume vertex A has degree 4. Let's assume vertex A has degree 4. Now you notice one thing. That this vertex has a degree 4. In worst case, which color number I need for A? In worst case, which color number I need for A? Okay, see, there are 4 neighbors. Right? There are 4 neighbors. Which is the lowest number available for A in worst case? In worst case, which number is available for A? In worst case, that is 5. In worst case, 5 is available. In worst case, 5 is available, or 1 to 5 is definitely available. Yes or no? In worst case, 1 to 5 is definitely available. Because notice that, okay, this has 4 neighbors. For example, let's assume that let's assume this has 1, this has 2, this has 3, this has 4, then in worst case this 5 number is available. So can you notice that in this graph, to any vertex you will always give color from 1 to 5. For example, maybe this is your vertex, and maybe the situation is like this. Just think about it and tell me. Maybe the situation is like this. To this the vertex number, okay, this has 3, this has 3, and this has 4. Then what color I will give to A? In this situation, what color you will give to A? The greedy algorithm. Tell me. Hi everyone. So what color you will give to A? In this situation, the color number 1, which color you will give? You will give color number 1 because this is the minimum color available. This is the minimum color available. In this situation, which color number you will give? 1. Okay, so let's assume in this situation, which color you will give? Like let's assume that you have 2, 4, 1, 5. Then what color you will give to A? What color you will give to A? You will give color number 3. Okay, so you can notice this is what I am saying. See, very simple point. Very simple point that, for example, let's assume 4. Okay, so let's assume these colors are there. Like, okay, 3, 5, 2, 1. So in this situation, what color you will give? You will give color number 4. So this is what I'm saying. Very simple point. So you can notice if your chromatic, remember, so this is the note. Very simple point that if G has maximum degree 4, if maximum degree of G is D, if maximum degree is D, or I can say if maximum degree is delta, then one thing you can notice that if maximum degree is delta, then I can say chromatic number will be definitely less than equal to delta plus 1. Definitely it will be less than equal to delta plus 1. I can guarantee that the chromatic number will be less than equal to delta plus 1. Why? What is the reason? What is the reason? Because any vertex you take, it will definitely get, okay, any vertex you take, it will definitely get color from where to where? It will definitely get color, okay, color between 1 to delta. Okay, it will definitely get color between 1 to delta plus 1. 1 to delta plus 1. In worst case, what can happen? In worst case, the neighbors can have different colors. In worst case, the neighbors can have different colors. So this will get delta plus 1. Is this clear? Let me know. Is this clear to everyone? So definitely it will get, okay, definitely it will get color between 1 to delta plus 1. So any vertex you take, that will get color between 1 to delta plus 1. In worst case, these vertices can have delta. In worst case, then this vertex will have delta plus 1. To how many people this is clear? Let me know. Is this clear to everyone? Okay. So from the greedy algorithm, very simple. This point is very simple because in worst case, all the neighbors, they can have different colors. In worst case, they can have different colors. Then in this case, definitely you will get color from 1 to delta plus 1. And this point is basically, sometimes you can use this. If you know the maximum degree, then you can guarantee that this will be less than equal to delta plus 1. So this is the idea. For any graph, remember, for any graph, the chromatic number will be less than equal to delta plus 1. So the greedy algorithm we have already seen. What is a greedy algorithm? Let's see this question. For this question, again, the same thing what we will do, we will apply the greedy algorithm. Let's apply the greedy algorithm for this question. If I apply this in this order, okay, let me apply the greedy algorithm and let me apply in this order. Let me start from A. Then what I will do, I will give color number 1. Let me go to E. Then what I will do, I will give color number 2. Let me go to F. What I will do, Which color I will give to F? I can reuse color number 1. Value 1 is available. I will use value 1. Then let me go to D. Which value I will use? Value 2 I will use. Then let me go to B. Let me go to B. Which value I will use? Let me go to B. So I will use 3 because, okay. So after D, I am going to B. So I will use 3. Okay. Now let me go to C. Which value is available? Which value is available for C? Which value is available for C? I cannot use 1. I cannot use 2. I cannot use 3. Which value is available? Value is available is 4. Okay. So that's the idea. So can I say chromatic number is 4? Can I say chromatic number is 4? Can I say chromatic number will be 4? No, because I told you greedy algorithm does not give you chromatic number. So can I, if you say chromatic number is 4, if you say chromatic number is 4, this is wrong. This is absolutely wrong. Because greedy algorithm does not give you chromatic number. This greedy algorithm says that this graph is 4 colorable. This greedy algorithm says that this graph is 4 colorable. So it means what is your chromatic number? It means your chromatic number is what? It means your chromatic number is less than equal to 4. It means your chromatic number will be less than equal to 4. But remember, can we do it? Can we do this graph using 3 colors? So we already know 4 colors is fine. 4 color is good. But can we use only 3 colors? Can we do this graph using only 3 colors? Very important point you notice here. This is a triangle. So can I guarantee at least 3 colors? This is a triangle. So can I guarantee at least 3 colors? So remember, because this is a triangle, so I can guarantee they will get different colors. I can guarantee they will get different color. This guarantee I can give. Okay, this guarantee I can give that they will get different colors. So what do? You apply like this because you start from triangle. Very simple point. You start with the triangle. Basically, you start with complete graph. You start with the largest complete graph. Yes or no? You start with largest complete graph. And in this graph, what is the largest complete subgraph? You start with largest complete subgraph. So like this is a largest complete subgraph. You don't have K4. You don't have K4. So the largest complete subgraph is basically here. In this graph, the largest complete subgraph is K4. In this graph, that is K3. That is K3. So 3 colors is definitely needed. So you start like this. Now tell me, can I use color number 2 here? Now can I use color number 2? Yes, I can use color number 2. Okay. Can I use color number 3? Okay, I cannot use color number 2. I cannot use color number 1. I can use color number 3. And here I can use color number 1. So this will tell me this is, can I say chromatic number is 3? Can I say chromatic number is 3? No. Again, no. Don't say chromatic number is 3. Again, you know that this is 3 colorable. You know this is 3 colorable. Now you can guarantee that chromatic number is 3. How can you guarantee? How can you guarantee that chromatic number is 3? Because this triangle will need 3. Okay, this triangle, if you notice this triangle will definitely need at least 3. Okay, so this BCD triangle, because of this BCD triangle, the chromatic number will be greater than equal to 3. And this is saying the chromatic number will be less than equal to 3. And so these two means chromatic number will be 3. So for this graph, the chromatic number is 3. Is this clear to everyone? Let me know. So remember, greedy algorithm के भरोसे मत बैठो. Okay, there is a dialogue, there is a meme. Greedy algorithm के भरोसे मत बैठो, क्या पता वो तुम्हारे भरोसे बैठी हो. Which movie? Do you remember the movie? Mansi, right? There is a dialogue. भगवान के भरोसे मत बैठो, क्या पता भगवान तुम्हारे भरोसे बैठो. Okay, so anyway, so this is the idea. So the answer will be 3. So this is how you can find. So okay, let's see the guidelines. Before we see the guideline, tell me one thing. What is the relation between chromatic number and clique number? Relation between chromatic number and clique number. What can you say about that? What is the relationship between chromatic number and clique number? This is your chromatic number. This is the chromatic number, and this is the click number. What is the relation? Anyone? What is the relation between these two? Yes, very good. So chromatic number will definitely be greater than or equal to click number. Okay, and the idea is very simple, because click number means what? Click number means what? This is the largest complete subgraph. Yes or no? This is the largest complete subgraph. Very simple. Click number is basically the largest complete subgraph. So if your largest complete subgraph has size k, just think about it. Okay, let's assume you have a graph G. You have a graph G. Okay, in this graph G, let's assume in G the largest complete subgraph has size P. Okay, maybe the largest if the largest complete subgraph in this the largest complete in this graph the largest complete subgraph has let's assume k vertices, or maybe has let's assume m vertices, then has m vertices. If the largest complete subgraph has m vertices, then what it means? It means your click number is what? It means your click number is what? The largest complete subgraph has m vertices, then it means your click number is m. And because this is a complete subgraph, so how many colors you need? Because this is a complete subgraph on n vertices, m vertices, so definitely what you need? So the chromatic number will definitely be greater than equal to m. Definitely at least m colors you need. Okay, so so I can say the chromatic number will definitely be greater than equal to m. So this is the idea. The chromatic number is always greater than equal to the click number. This is the idea. Yes or no? This is the relationship between chromatic number and the click number. Is this clear? Now let me tell you the guidelines to find chromatic number. These are only guidelines to find chromatic number. If you want to find chromatic number, then these are the guidelines. What is the first guideline? The first guideline is very simple. If standard graph, you do directly know the answer. Yes or no? If standard graph, if your graph is standard, what are the standard graphs? Can anyone tell me what are the standard graphs? Like Kn, okay, like bipartite graph Kmn, okay. So like these graphs like Pn, like Cn, like Qn, okay, like En. So these graphs, very simple. So these are the standard graphs. So if you have a standard graph, then you directly know the answer. Then you know the answer. Okay. Then second, what is the second? Basically find click number. Find largest complete subgraph. Find largest complete subgraph. You start with there. Find largest complete subgraph and start from there. And start coloring from there. And directly give different colors to these vertices. And start coloring from there. And start coloring from here. Okay, so directly give different colors to those vertices. Is this clear? So very simple. Find largest complete subgraph, and then what you do? You start your coloring procedure from the largest complete subgraph. What you do? You start your this coloring procedure, and what you do? Directly give different colors to all vertices. Directly give different colors to all vertices. To all its vertices. Okay, so this is the idea. This is your now this for example, remember what are the examples? So you can find, for example, if you you can find maybe you can find K4. For example, let's assume this is the largest. If this is the largest complete subgraph, if you find a K4 and this is your largest, you cannot find bigger than this. Means let's assume this is the largest complete subgraph. Then what it means? It simply means that you start from here. It simply means chromatic number will be less than greater than equal to 4. So basically, if this is the largest complete subgraph, so you start with it. Start coloring here. Start coloring with it. Okay, so this is the idea. Now if you don't have a complete graph, if you don't have K4, then what do you look for? This is the third guideline. Okay, if no K4, if no, I can say if no Kn, basically if no Kn subgraph, if no Kn subgraph, then what you do? Then find odd cycles. Then find odd cycle. Then find odd cycle. Why odd cycle? Tell me. Then find odd cycle. Because odd cycle needs how many colors? Okay, this odd cycle needs at least 3 colors. Okay, so it needs at least 3 colors. It definitely needs at least 3 colors. So this odd cycle will tell you that, okay, at least 3 colors is needed. So you find odd cycle, and what you can guarantee that chromatic. Okay, is this clear? So when find the largest complete subgraph, and if you find the largest complete subgraph, then you can start with it. Then you find what? Then you find odd cycle. No, but Nikhil, C5 did not cover. C5, C7, they did not cover. Nikhil, C5, C7. We did not cover C5, C7. Okay, so find odd cycle. Mainly what cycle you will try to find? Which cycle you will try to find? C3, C5. These cycles you will try to find mainly. C3, C5. Okay, so this is the idea. And what is the fourth guideline? The fourth guideline is, once you get the answer, okay, these things you can apply. Okay, the fourth guideline is these things you can apply, that chromatic number will be less than equal to delta plus 1, and it will be greater than equal to the clique number. So these things you can apply. The chromatic number will definitely be between these two. Okay, so this you can apply. And what is the fifth? And this is very important point, because many students make mistake in this point. What is the answer? Once you get answer, once you think, once you get answer, okay, once you get answer, once you get answer K, once you get this answer K, ask yourself, is it minimum? Can you do better? Ask yourself, can you do better? Can you do with less than K? Okay, is this clear? So once you get your answer, remember, once you get your answer, then ask yourself, can you do with less than K? And the sixth is practice, practice, practice. Okay, practice, practice, practice. So anyway, we will do a lot of practice, and all these guidelines we will use. All these guidelines that I've told you, we will use these guidelines, and you don't have to worry. But this point is important. Once you get the answer, then ask yourself, can you do better than this? Can you do better than this? Okay, so this is what you have to ask. For example, this graph. Tell me, from where should I start? For this graph, let's find out the chromatic number. So which guideline I will use? Do I have K4? In this graph, do we have K4? Is there any K4? There is no K4. Do we have cycle, odd cycle? Do we have an odd cycle? Like any odd cycle do we have? Is there any odd cycle like C3? Do we have triangle? I don't think there is a triangle. Okay, so there is no triangle. Okay, so anyway, so let's start then. Okay, because their guidelines are not working for this graph. Guidelines are not working. So let's start. So let me give color number 1 here. Let me start here. Let me give color number 1 here. Then what I can do? I cannot use this color number 1 here. So I can use color number 2 here. I can reuse color number 1 here. Okay, I can reuse color number 2 here. I can reuse color number 2 here. Use color number 1 here. So what I got? What answer I got? I got 2 colorable. What answer I got? I got 2 colorable. But can I guarantee? Okay, remember this. I will ask myself, what I will ask? I will ask, can I do better than 2? Can I do better than 2? Tell me, can I do better than 2? No, you cannot do better than 2 because you have at least one edge. So definitely you need at least 2 colors. You need at least 2 colors. Okay, cannot do better. So I can say cannot do better. Cannot do better. So finally answer will be what? Chromatic number is 2. Okay, for this graph, chromatic number is 2. So like this you can do. Let's see the next question. Okay, so the chromatic number is 2, you can see. Okay, for this question, what should I do? For this question, from where should I start? I will see this K4. I can see this K4. I found K4. Okay, so once you find K4, array, Preeti, K4. I already have K4. If I have K4, then why I care about odd cycle? I have Hukum ka patta, you know, so I have this K4. So what I will do? I will start directly. I will start directly 1, 2, 3, 4. No problem. Okay, so there is no problem. 1, 2, 3, 4. Now reuse. Now reuse. So I can reuse color number 2. Now reuse color number 1. Now reuse color number 4. So finally, I got 4 colorable. I got 4 colorable. Can I guarantee? Can I do better? I got 4 colorable. Can I do better? Cannot do better. Cannot do better. Okay, because of this, I cannot do better. So finally, the chromatic number will be 4. Okay, you cannot do better because this is already K4. This needs, okay, this needs at least 4 colors. I can say because of this, we need at least 4 colors. Because of this, at least 4 colors you definitely need because of this. Okay, so that is the reason answer will be 4. Let's see this. This. Okay, let's see this graph. What do you think? Do we have a triangle? First of all, okay, there is no K4. We don't have any K4. But do we have a triangle? Yes, there is a triangle. There is a triangle. You can notice ECF. ECF. This is a triangle. So, okay, you got a triangle. You got a C3. What is a C3? Okay, so this is your C3 you got. Or I can say this is your C3, ABD. This ABD C3 you got. Okay, A, B, D. This ABD C3 you got. So once you got this ABD C3, odd cycle, Arpan, we care about odd cycle. Odd cycle will, see, C4 will give you 2, C3 will give you 3. So we care about odd cycle. We don't care about even cycle. We care only about odd cycle. So this ABD we got. Okay, so directly give 3 different colors. ABD, directly give 3 different colors. Because this is an odd cycle. So it definitely, because of this chromatic number will definitely be greater than equal to 3. The chromatic number will definitely be greater than equal to 3. Now, can I do using only 3? So I can give color number 3. I can reuse color number 3. I can reuse color number 3, right? I can reuse. Okay, so here, color number 3 I can reuse. Color number 1 I can reuse here. And color number 2 I can reuse here. Okay, so the answer will be what? So the answer will be, okay, 3 colorable. So this is giving me 3 colorable. Okay, so 3 colorable means, what 3 colorable means? Can anyone tell me? What 3 colorable means? 3 colorable means the chromatic number is less than equal to 3. Okay, so from this and from this, I can say chromatic number is 3. I can guarantee chromatic number is 3. Okay, is this clear to everyone? All these questions. So did you understand the chromatic number? Did you understand the concept of coloring? We have seen every variation, everything we have seen. Did you understand? Okay, so let's see this GATE 2002 question. What will be the answer for this? The minimum number of colors required to color the vertices of a cycle of n nodes such that two adjacent nodes no two adjacent nodes have same color. So this is your coloring problem. No two adjacent nodes should have same color. This is your vertex coloring problem. Okay, and you have a cycle of basically Cn. For Cn, you know the answer. The answer will be 2 if n is even. The answer will be 3 if n is odd. So which option is correct? Definitely this option is not correct, not correct, not correct. So the answer will be what? The answer will be option D. Actually, this is a beautiful question, because if you notice this value, this will become 3 for n equal to odd. This will become 2 for n equal to even. If you notice this, n minus, if you notice this is your expression. Let's call it this expression E. So this is your n minus 2, n by 2, okay, plus 2. So this, if you notice that this, what will happen here? If n is even, then what will happen? For example, if n is even, like if you take n equal to 6, then what will happen? If n is even, then what will happen? Then you will get what? So for example, if you put n equal to, okay, so then you will get e equal to 2. Then you will get 2. And if you have n equal to odd, for example, let's assume 7. If you have n equal to odd, 7 if you take, then what you will get? Then you will get it 3. So this value, remember this value becomes 3. This becomes 2 when n is even, and this becomes 3 when n is odd. So this is your answer. Answer will be option D. Can you notice from this question, can you observe one thing about GATE exam? Please make one observation about GATE exam. GATE exam is basically all about these things. See, this thing is known to many people. Many people know this thing. But here, if they give nice options, like instead of these options, they should give nice options. Like this type of options they should give. This type of options they can give. Yes or no? This type of complicated options they can give. They can give. So this is what I'm saying. So this is the beauty of GATE exam. In the GATE exam, you have to apply your brain. If you by heart this, it will not help you, because another option can be, for example, they can change the option. They can change the option, and another option will be like this: 2, okay, n by 2 seal plus 2. Another option will be something else. Another option will be something else. So you have to find out. So the answer will be this, option D. Let's see this question. Okay, so tell me, from where to start for this graph? From where to start? There is, do we have K4? Do we have K4 in this graph? No, we don't have K4. There is no K4, but we have a triangle. But we have this triangle C3. Okay, so let's start with this C3. So I can start like this: 1, 2, 3. Okay, very simple. 1, 2, 3. 1, 2, 3. Okay, now what? Now what? Okay, so now you can reuse the color. This color number 1 you can reuse. Okay, this color number 1 you can reuse. Actually, what you can do, you can use, see, you can use color number 3 here, color number 1 here, color number 2 here. This is what you can do. Okay, and then whatever I do, I need color number 4 here. Then I can use color number 4 here. So I have a 4 colorable. So I have 4 coloring. I know 4 colorable I have, but can I do better than this? Can I do better than this? I have 4 colorable, but can we do better than this? See, you cannot do better than this. You cannot do better than this, because notice what will happen. See what will happen. See, here you will give 2 different, see, here you will give 3 different colors. Now, if I do, for example, if I give color number 3 here, if I give color number 3 here, now I can give color number 1 here. I can give color number 2 here. Now notice here I cannot give color number 1, 2, 3. Now again I have to use color number 4, and then I can use color number 1. Then I can use color number. I have to use color number 4. And now which color I can use here? Okay, actually this, like this, if I do, then I will get 5 colorable. Like this, if I do, I will get 5 colorable. But ask yourself, can you do better? If I do like this, so it means chromatic number is less than equal to 5. Can we do using 4 colors? Yes, we can do using 4 colors. You can check it. This is the best you can do. You cannot do better than this. Okay, so actually cannot do better. Actually for this question, you have to try, you have to check, see, if you get the answer 5, then you try. For example, you get the answer 5. Let's assume you get the answer 5. Then you do better. Then you ask, can you do better? Can you do better? Okay, so this is what you ask. Can you do better? Now you can notice that, yes, you can do better. But now, can you again do better? Can you again do better? Actually, you can try. Okay, you can try in some 2-3 ways. You can try, and you will see that you cannot do better. You can try. Okay, basically you can try, but okay, cannot do better. Okay, so finally I can say the chromatic number will be 4 for this question. Okay, so you have to try. Basically for this question you have to try. Let's see this question. This is your GATE 2006. What is the answer? So the question is saying that there is a graph, and in the graph vertices are bit strings of length n. The vertices, they are the bit strings of length n, bit strings of length n. We have edges between two vertices if and only if they differ in exactly 1 bit position. They differ in exactly 1 bit position, exactly 1 bit position. So what is your graph G? Can you notice? What is your graph G? This is your hypercube graph. Yes, the definition of hypercube graph is given to you. This is GATE exam. This is GATE exam. See, let me tell you why this question is important. See, many people, they by heart notes. Okay, there are many people you will find what they will do. They will take some notes and they will by heart those notes. In those notes, it will be written. What will be written? In those notes, it will be written that Qn, okay, facts of Qn will be written. All the facts. You will see many people teach like this. Yes or no? Many people, what they will do? They will write facts, back to back facts. There will be 10 facts. Okay, and these facts you will by heart. If you by heart these facts, okay, then you cannot solve this question. Then you cannot solve this question. First, you have to understand what is this Qn, that this graph is Qn. Okay, so never do this. Anyway, so let's come back to this question. So this is your graph G, and this G is basically your hypercube graph on n vertices. Because there are how many vertices? Sorry, this is your hypercube graph Qn. Because in hypercube graph we have strings of length n. How many vertices? Can anyone tell me how many vertices? There will be 2 power n vertices. You already know this. Now tell me, in the question, the ratio of chromatic number and diameter. What is the chromatic number of Qn? The chromatic number is 2. And what is the diameter? We have already seen diameter. We have already seen diameter. Diameter is n. So the answer will be 2 divided by n. The diameter we know, right? Kusal, we know the diameter, because what will be the diameter? From this edge, from this to this, the path length, the distance will be 3. The distance will be 3. So this was the diameter. So the answer will be what? So chromatic number to diameter, the answer will be 2 divided by n. Is it clear? So like this. This is another question, GATE exam question. So what is the answer for this? What is the chromatic number of the following graph? For this graph. In this graph, do you have odd cycle? Do we have odd cycle in this graph? Yes, there is a odd cycle. See, this is the odd cycle. This is the C5. This is the C5, C5, C5. You got your C5. So you can notice this is your C5. These 5 vertices are giving you C5. So this is giving you C5. And so because it is C5, so what can you say about chromatic number? At least 3 you need. This is C5, right? A, B, C, D, E, A. A, B, C, D, E, A. Okay, this is your C5. A, B, C, D, E, A. So finally, what I can say, the chromatic number is at least 3. So give 3 colors. Okay, so let's start with this. Let's give three colors: color number 1, color number 2, color number 1, color number 2, color number 3. I cannot give color number 1 here. Can I give color number 1 here? Can I give this? No, because these are adjacent. Okay, so I cannot give color number 1, color number 3. Now, can I reuse the colors? Can I reuse? Yes, color number 2 I can use. Yes, color number 1 I can use here. Yes, color number 1 I can use. And what about this point? So I can use color number 2. Okay, so the answer will be 3. And okay, so this is 3 colorable. So we got 3 colorable. Can I guarantee at least? Okay, can I guarantee 3 colorable means chromatic number is less than equal to 3? Okay, and this is saying chromatic number is greater than equal to 3. So finally I can say chromatic number will be 3. I can guarantee 3. Okay, this is another question, GATE exam, GATE 2009. What is the answer for this question? The chromatic number of a n vertex simple connected graph, n is greater than equal to n is greater than 2. N vertex simple connected graph, which does not contain any odd length cycle. It means your graph is what? It means your graph is what? Your graph is bipartite. Your graph is bipartite. For bipartite, what should be the answer? For bipartite, what should be the answer? The answer should be at most 2. The answer should be at most 2. The answer should be at most 2. But why the answer is exactly 2? Here the answer will be exactly 2. Why? Because n is greater than equal to 2. Okay, remember, n is greater than 2 and connected. These words are very important. Okay, connected and greater than 2. Okay, so these two things means at least one edge. These two things means at least one edge. We have at least one edge. So that is the reason chromatic number will be greater than equal to 2. So chromatic number will be greater than equal to 2, less than equal to 2. So finally I can say chromatic number will be 2. Why this is bipartite? Because there is no odd cycle. A graph is bipartite if and only if there is no odd cycle. Bani, a graph is bipartite. We have already seen this is important theorem. A graph is bipartite if and only if no odd length cycle. Another statement, the graph is bipartite if and only if every cycle has even length. The same statement I can write like this: a graph is bipartite if and only if every cycle has even length. Every cycle has even length. Okay, every cycle has even length. So this is the idea. So this graph is bipartite, and you can notice that because it is connected and n is greater than equal to n is greater than 2, so there is at least one edge. So that is the reason I can say chromatic number will be 2. Okay. In this same question, if I remove this, and if I say n is greater than, if I say n is greater than equal to 1, then remember the answer will be at most 2. Then for this question, and if options are like this, let's assume options are like this. Let us assume options are like this. Then the answer will be option B. Because you know, if you have n equal to 1, then the chromatic number will be simply 1. Okay, so this is the idea. And this is the GATE exam question. This we have already seen in this class. Already we have seen. So I told you that for this question, what will be the answer? What will you do? You will start with the cycle. What will you do? You will start with the C3. This C3 I can see. So what you will do? You will start with here. 1, 2, 3. These 3 you can give. 1, 2, 3. Okay. So because we have a cycle, this cycle we have. Now, can I reuse? Yes, color number 2 I can reuse. Color number 1 I can reuse. Next, color number 1. Next, what I should do here? Next, if I do like this, then what I will get? Color number 2 I cannot use. Color number 1. Okay, so then I will get 4. But can I do better? So I got 4 colorable. What I got? I got 4 colorable. I got 4 colorable. But can we do better? Can we do better? The question is always, remember 4 colorable means chromatic number is less than equal to 4. But the question is, can we do better? Can we do better than this? Always ask, can we do better than this? So yes, we can do. See, again, you start from this 1, 2, 3. But what you do after this, if you take this, because I can reuse this color number 2. After this, if you take this, okay, and you can use color number 3 here, and you can use color number 1 here. So yes, we can do better. Yes or no? See the problem. What is the problem here? The problem this is happening that because of these vertices, we have to give 4 here. But if you directly give, for example, this color number 2 I can use here, this color number 1 I can use here. Okay, then I can use color number 3 here. So now we have a 3 colorable. Now what we have? We have 3 colorable. It means chromatic number is what? Less than equal to 3. Can we do better? Can we do better? No, there is a cycle. There is C3 here. So there is C3 here, and this C3 means you need at least 3 colors. Okay, so these 2 points means the chromatic number will be 3. So we have seen all the questions, everything we have seen. For this question, what will be the answer? So color the vertices with as few colors as possible. Okay, minimum number of colors you need. So what should be the answer for this question? So again, there is a cycle. You can see there is a cycle. So you can start 1, 2, 3. You can start with 1, 2, 3. Then what you can do? Then you can reuse color number 2 here. You can reuse color number 3 here. You can reuse color number 1 here. So the chromatic number here will be 3. Okay. You can guarantee 3 because there is a cycle. Because there is a C3, so you can guarantee that the chromatic number will be greater than equal to 3. You can guarantee. And because we got 3 colorable, the graph we got is 3 colorable. It means the chromatic number is less than equal to 3. So finally, I can say the chromatic number will be 4. Okay, so from these two, from this and from this, I can say the chromatic number will be 3. So you can notice this is the definition of chromatic number. Chromatic number is the minimum number of colors needed. Okay, and you already know that if G is K colorable, then chromatic number will be less than equal to K. If G is K chromatic means chromatic number is K. K chromatic means chromatic number is K. K colorable means chromatic number is at most K. So this is the idea. Okay. So all the things we have seen, this thing we have seen. If G is a graph, then chromatic number will definitely be what? Greater than equal to clique number. So this equation we have that chromatic number will be between clique number and this maximum degree plus 1. So between that. One last thing, actually, one very interesting thing we need to see. What can you say about if, okay, this is my question. Okay, let's assume you have a graph G. Let us assume you have a graph G and this is properly colored. Let's assume this is properly colored. Then a particular, okay, then vertices of a particular color, what they will create? This is properly colored. Then vertices of a vertices, all vertices of a particular. So vertices of a particular color, what they will create? Okay, forms. What they create? What they create? They will create independent set. Very good, because they are non-adjacent of a particular color. Like particular color, for example, red color. So if you are giving red color, it means what? It means they are independent set. They don't have any edge. Because you are giving red color, it means what? It means what? If you are giving red color, it means what? They are non-adjacent. They are pairwise non-adjacent. So they are independent set. So they will create independent set. Very simple. So remember, if you notice the color classes, what are the color classes? What are the color classes? What is that? Color classes means like this. What you do? You have a graph G. Okay, color classes means what you do? So these vertices you can divide into color, like color classes. Like, okay, all the vertices of red color here. Okay, all the vertices of green color here. All the vertices of green color here. All the vertices of blue color here. Okay, and so on, and so on. So you can notice this is called color classes. What you can do, all the red color vertices are here, all the red color vertices, all the green color vertices here, all the blue color vertices here. Now tell me one thing, is it possible that they have age? Is it possible there is any age? Is it possible there is any age? The answer is no. The answer is no. Is it possible there is any age? The answer is no. Is it possible there is any age here? There is any age here? Again, the answer is no. So this color class, if you notice, this will be an independent set. This will be an independent set. This will be an independent set. Okay, because this is the idea. Is it possible that there is age here? Is it possible there is age like this? Yes, this is possible. This is possible. There is no problem. These things are possible. These things are possible. These things are possible. So this is the idea. Okay, color classes. Now, very important point. Okay, few interesting things we will see. This is the question. If G has chromatic number, okay, if G has chromatic number, if G has chromatic number K, if G has chromatic number equal to, let's assume M, okay, if this is your chromatic number, then my question is, what can you say about number of edges? Then can I say number of edges will definitely be greater than equal to MC2? This is my question. Prove. Okay, then prove that number of edges will be, number of edges in G, number of edges in G, that will be greater than or equal to NC2. Let me tell you why. What is the reason? Let me tell you. See, very simple. The point is actually very simple. Just tell me this point. Chromatic number means what? Chromatic number is M. It means what? It means this is the minimum number of colors needed. It means this is the minimum number of colors needed. Yes or no? Number of colors needed means you cannot do better than this. Agree? Okay, agree. This is the idea. Chromatic number means minimum number of colors needed. So let's assume that these are your color classes. Let's assume your color classes like this. Okay, so for example, let's assume this chromatic number is 4. Let's assume. So let's assume your chromatic the color classes are like this. You have a red color here, you have green color here, and you have blue color here, and you have black color here. So let's assume this is the idea. Now tell me one thing. I'm asking, no, I'm asking Nikhil, I'm asking that at least these many edges will be there. Minimum number of edges, how many will be there? Minimum means this is the minimum number of edges. What it means? It means minimum number of edges. It means minimum number of edges in G. Remember this. It means minimum number of edges in G. Minimum number of edges in G is MC2. This is the minimum number of edges in G. But how to do this? Like minimum, how many edges you need? See, there is no edge here. 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 Is it possible you don't have any edge? Tell me one thing. Is it possible you don't have any edge? Is it possible there is no edge? Just tell me. Is it possible there is no edge? Is it possible there is no edge? Why? What will happen if there is no edge? If there is no edge, then what will be the contradiction? The contradiction will be this. This will be the contradiction. Because chromatic number is 4. If chromatic number is 4 means this is the minimum number of colors needed. So if you don't have any edge, let's assume there is no edge. Let's assume there is no edge. Then the chromatic number should be 1. Okay. So there is a contradiction. If you don't have any edge, there is a contradiction. I can say if you don't have any edge, then there is a contradiction. If you don't have any edge, no edge implies contradiction. Okay, so there is no, okay, that is a contradiction. What will be the contradiction? The contradiction will be that zeta will be 1, but but already zeta is 4. Okay, so there is a contradiction. Another thing, tell me another thing. Is it possible there is no age between them? Is it possible there is no age between these two? Is it possible there is no age between these two? Between these two, there is no age. Like between these two, there is no age. Is it possible between these two, there is no age? If there is no age, then what is the problem? If there is no age, what is the problem? Tell me the problem. If there is no age between them, then you will merge. Then merge them. Then merge them. Then merge them. And the chromatic number will be what? The chromatic number will become 3, but chromatic number is 4. So again, there is a contradiction. So again, there is a contradiction. So then merge them. Okay, but okay, so this but is giving you contradiction. This is giving you contradiction. So what it means? It means, so final conclusion. Now tell me the final conclusion. The final conclusion is there is at least one age between every color class. There should be at least one age between every color class. This is the final conclusion. At least one age should be there. At least one age should be there between every color class. Between every color class, at least one age should be there. At least one age. So minimum number of edges I am asking. I am asking minimum number of edges between every color class. At least one age should be there. Agree or not? So between every color class, okay, remember, between every color class, at least one age must be there. At least one age must be there. Okay, between every color class in a minimum coloring. Okay, between every color class in minimum coloring. In minimum coloring. If your coloring is minimum, then this should happen. Remember, if your coloring is not minimum, then this will not happen. See, if your coloring is minimum, A, B, C, D. If your coloring is minimum, like red, okay, like if you have this coloring, green. So here your coloring is minimum. This is a minimum coloring, correct? This is a minimum coloring. And because this is a minimum coloring, so you can notice these are the red vertices, A, D. These are the red vertices. And these are the green vertices, B, C. And you can notice, because this is the minimum coloring, so there is at least one edge. This is independent set. This is independent set. And there is at least one edge. There is at least one edge. I can say there is at least one edge. You have at least one edge. Okay, there can be more than one, but there is at least one edge. Okay, so this is the idea. At least one edge is there. But remember, if you don't do minimum coloring, then this is not guaranteed. If you don't do minimum coloring, for example, color number 1 here, color number 2 here, color number 3 here, color number 4 here, then color number 1, who are the color, like, okay, maybe red, let me give some other color, like, okay, red color here, green color here, blue color here, and some other, I'm forgetting colors, yellow, okay, yellow color here. So you can notice here now red color is this, the green color is this is the color class, the blue color class is this, and the yellow color class is this. Now there is no guarantee, yes or no. Now this is not minimum coloring. This is not minimum coloring. Now you can notice there is no age between these two. For example, there is no age. You can notice there is no age. So are you getting my point? So if you have between every color class, in a minimum coloring, this is important, in a minimum coloring, okay, at least one must be there between every. So what can I say about number of edges? At least how many edges must be there? At least how many edges must be there? So chromatic number C2. Yes or no? Between every two there should be. Okay, so there are how many color classes are there? How many color classes? These many color classes. These many color classes you have. Chromatic number. This chromatic number is equal to the number of color classes. So the number of color classes will be zeta. And between every two color classes, you must have at least one edge. Between every two of them. So, okay, so minimum these many colors will be, minimum these many edges will be there. Is it clear? Let me know. Is this clear to everyone? How many of you got it? Did you understand this? Let me know. Please let me know if you have doubt. Do you have doubt? Any doubt in this? Okay. So very simple. Now, maximum how many edges can be there? This is the next question. If your graph is like this, okay, then what is the maximum how many edges can be there? Your graph is this, and let's assume this has chromatic number is this. This zeta is the chromatic number. Okay, this is your chromatic number. If this is your chromatic number, then what is the maximum number of edges you can have? Maximum number of edges. What is the maximum number of edges? Very simple. Maximum number of edges. This is actually very simple because these are, let's assume these are your color classes. Your color classes are these. For example, red, these are the red. Okay, and these are the green. Okay, and so on. Okay, and so on. So, okay, you can notice one thing, that if your chromatic number is this, if your chromatic number is this, then maximum how many edges you can get? Maximum how many edges you can get? So to get maximum, what you will do? See, to get maximum, you can notice if there are some vertices here, then they are independent set, right? They are independent set. They are independent set. Okay, so for every color class, any color class you take, any color class you take, that does not have any edge. There is no edge here. There is no edge here because these are the red, so there is no edge here. Similarly, this is independent set, so there is no edge here. So if you want maximum number of edges, then what you will do? Between every vertex of this and every vertex of this, there will be edges. Okay, this is what you will do. This is what you will create. This is what you will create. Okay, you will create like this. This type of situation you will create, right? Okay, right, like this. This type of situation you will create. Agree? Do you agree? Okay, so basically, actually, we cannot find because we need the data. We need how many vertices are here, how many vertices are here, how many vertices are here. This data we need. But I am saying that to get maximum, this is what you can do. For example, okay, let's assume that you have a graph G, and in this graph G, let's assume there are 20 vertices. Let's assume there are 20 vertices, and let's assume this for this graph, the chromatic number is 4. And these are the 4 color classes. You have total 4 color classes red. In this color class, let's assume there are 5 vertices. Okay, and there is yellow. In this color class, let's assume there are 4 vertices. And there is green. In this color class, let's assume there are 2 vertices. And there is blue. So how many are remaining? So let's assume there are 9 vertices. Okay, now tell me what is the maximum number of edges? So what is the maximum number of edges will be there? What is the maximum number of edges now? So very simple. So what you will do? Between every vertex of this and every vertex of this, there will be edge. Yes or no? Between every vertex of red and yellow, this is what you will do. For red comma yellow, what you can do? For every pair of vertices, you will create edge. You can take one vertex from here, one vertex from here, and you will create edge. So how many edges you can create? Tell me. So how many edges you can create? These many edges, these two will create. These many edges, these two will create, like red and yellow. Okay, similarly, this red and green, how many edges they will create? How many edges they will create? So you can notice between every two vertices here, you will create edge. So there will be 10 edges. There will be 10 edges like this. So finally answer will be what? So the final answer will be what? Let's see, because of red you are getting, okay, if you notice, because of red you are getting 5 into 4, 5 into 2, 5 into 9. So this is what you will get: 5 into 4 plus 5 into 2 plus 5 into 9. This you will get because of red ones. Next, because of yellow ones, what you will get? This yellow one is counted here. So because of the yellow ones, what you will get? You will get 4 into 2, 4 into 9. 4 into 2, 4 into 9. Okay, what is remaining? Green ones, 2 into 9. 2 into 9. So this will be your answer. You can add all of them. That will be your final answer. Is it clear to everyone? So remember, if I ask you maximum number of edges, then what you will do? Remember, this is independent set. This red is independent set. This yellow and this green is also independent set. So there is no edge. There is no edge between these 5 vertices. Between these 5 vertices, there is no edge. These 5 vertices, they are independent set. These 5 vertices are independent set. But between these color classes, you can make all the possible edges. All the possible edges you can make between these color classes. So this is the idea. So you can notice minimum how many edges will be there? These many. We have already seen. What is the logic? One line. In one line, what is the logic for this? What is the logic for this in one line? How many edges? Minimum how many edges will be there? That is chromatic number C2. That is chromatic number C2. And that is same as chromatic number into chromatic number -1 divided by 2. And what was the logic for this whole thing? What was the logic? The logic is between every color class, at least one edge must be there. At least one edge between every pair of color class. Very good. Yuvraj, very good. Excellent. Okay. So that's it. And this is also very easy. This is another very easy thing. Let's see the proof for this. This is actually very easy. So tell me one thing. If you have a graph, and let's assume in this graph, the chromatic number is this. This is the chromatic number. If this is the chromatic number, then what can you say about the largest? Okay, what can you say about size of? What can you say about size of largest color class? So what is the size of largest color class? Like size of average color class. Tell me, average, like at least one color class you will have, right? Yes or no? Size of average color class. What that will be? Size of average color class. What that will be? You have these many color classes. So average color class size will be what? That will be number of vertices divided by zeta. Number of vertices divided by zeta. Because these are your color classes. Your color classes are like red, green, okay, blue, and so on. And so on. These are your color classes. Some vertices are here, some vertices are here, some vertices here, and so on. So size of average color class, like on average, what is the size of a color class? That will be this. Yes or no? On average. On average. Okay, so can I say there is at least one color class with these many vertices? Can I say there is at least one color class with these many vertices? Okay, so there is at least one color class. So there is at least one color class with, remember, there is at least one color class with how many? There is at least one color class with these many vertices, with this average number of vertices, right? With average number of vertices, with average number of vertices. Okay, with at least these many vertices, with at least average number of vertices. Is this clear? This is the meaning of average, right? If average is this value, if average value is, for example, if average value is k, what it means? It means there is at least one person less than equal to k. There is at least one person greater than equal to k. Yes or no? This is the meaning of average. That is the meaning of average. Like someone is small, someone is bigger, small, bigger, small, bigger. So the average meaning is this. So I can say that there is at least one color class. At least one color class will have at least these many edges, these many vertices. Okay, and this color class, this is an independent set. So what can you say about independent set? What can you say about independence number? This is independent set. You know, this is independent set. This is independent set. So what can you say about independence number? So finally, what can I say about independence number? That should be greater than equal to this. Independence number should be greater than equal to this, isn't it? Because this is already independent set. See, this color class, this is already independent set. This color class is already independent set, and this color class has these many vertices. At least these many vertices. At least these many vertices are there. Okay, at least, maybe more, maybe more. More than this can be there. Okay, maybe more. At least these many vertices this color class has. This color class is independent set. So we have an independent set. We have an independent set with at least these many vertices. We have independent set. This independent set we have with at least these many vertices. So what can we say about independence number? So the largest independent set, that will be greater than equal to this. So I can say alpha is greater than equal to number of vertices divided by zeta. And from this, what you got? If you simplify this, then what you will get? Then you will get alpha into zeta is then what you can say? Number of vertices is less than equal to alpha into zeta. The proof is clear. All these proofs, are they clear? See, these proofs are very easy. Okay, if you just apply the definitions, these proofs will improve your knowledge a lot of, like, whatever question comes in the GATE exam, whatever question, new question, any complicated question they give you, you can solve it. And these proofs are very easy, very basic things we are using. We are using the definitions, nothing else. Okay, is this clear? This proof is clear to how many people? So this is the idea. Okay, so these two things we have seen, and this is actually a TIFR question. Let me tell you, everything that we study that can come in the GATE exam, that can come in GATE exam or TIFR exam. See, this is the TIFR question. Now solve this question. Now solve this TIFR 2013 question. What this question is saying? There is a graph, undirected simple graph on n vertices. The definition of coloring is given. The coloring definition is given. Coloring is assignment of colors to each vertex such that endpoints of every edge have different colors. Endpoints of every edge are different colors. Yes, correct. Endpoints of different, if you have some edge, then endpoints must have different colors. They must have different colors. This is the definition of coloring. This zeta denotes the chromatic number, means the minimum number of colors needed in a valid coloring. This is the chromatic number. And this set B is given to you. This set B is independent set if no vertices are connected by an edge. This is the, okay. And this alpha is given to you. This is the size of largest possible independent set. Can you see this question is so well framed? Okay, like this type of questions, we love it. Like, okay, when you see this type of question, well framed, right? Every information you have, so you don't have any ambiguity. Every information is given. Chromatic number, coloring, independent set, okay, independence number, every information is given to you. There is no ambiguity. This is a very beautiful question. And this type of questions you will find in the test series also. GATEOverflow, goclass test series, the combined test series you can take. In that combined test series, you will see this type of well-framed questions. Every question. Okay, like, have you seen any test? Have you given any test? Every test has, well-framed question. There is no ambiguity in any question, right? You can check it out. Every question is well-framed. Okay, so you can, basically, you should definitely attempt GATEOverflow and goclass combined test series. You should definitely attempt. This type of nice questions you will find. Okay, anyway. Okay, so tell me now, what can you say? So you have independence number. So what we can say, we know that n is, we know, so what we know that alpha is bigger than n divided by chromatic number. This we have already seen. Alpha is bigger than, okay, and what is this? What is this? This is the average. This is the average size of color class. Color class. So, okay, so this is the average size of color class. And every color class is what? Every color class is independent set. So this is the average size of color class. This is the average size of color class. And every color class is independent set. So the largest independent set should be greater than equal to this. The largest independent set, that should be greater than equal to this. So the answer will be what? The answer will be option C. Is this clear? The answer will be option C. And this is another TIFR question. Tell me quickly, what is the answer? TIFR 2017. What should be the answer for this question? A vertex coloring of a graph with k colors. A vertex coloring of a graph with k colors. So this definition is given. The definition of vertex coloring is given, if you notice. See, the definition is given. Vertex coloring, the definition is given for vertex coloring, that a vertex coloring with k colors, that is a mapping. Means you are mapping the vertices into the colors. What you are doing? You are mapping the vertices to colors such that. If you have A's, then they have different labels. If you have A's, then they have different labels. See, this is the definition of coloring from as a function. This coloring as a function, you can think of coloring. This coloring you can think as a function. This coloring you can think as a function. So what you are doing? Basically your vertices. These are your vertices. 1, 2, 3, and so on. These are your vertices, and these are your colors. These are your colors, like red, okay, green, blue, and so on. So what you are doing? This coloring is basically, to every vertex, how many color we give? To one vertex, how many color we give? Tell me. To one vertex, how many color you give? Only one. Okay. And to every vertex, do we give a color? To every vertex, do we give a color? Do we give a color? Yes. So this is a function, right? Yes or no? This is a function, because every vertex should have exactly one color. Every vertex should have exactly one color. Should have exactly one color. Every vertex should have exactly one color. So this is a function. This is a function. And what is the condition for this function? This is your coloring function, I can say. This is your coloring function f. And what this function has the condition? What is the condition on this function f? This function f, this is from V to colors. From V to colors. And what we have? You can notice that if u comma v belong to age, if u comma v belong to age, if they have age, then what should happen? Then what should happen? Then fu should not be equal to fv, right? Yes or no? Then they should not get same color. fu should not be equal to fv. Agree? Yes or no? If two are adjacent, if they are adjacent, u comma v, if they are adjacent, then they should get different colors. If these two people are adjacent, then they should get different colors. So this is the definition of coloring as a function. Is this clear? Coloring as a function. Is this definition clear? That coloring is basically a function from vertices to colors. From vertices to colors. This is a function. Because every vertex should get exactly one color. To every vertex we give exactly one color. So this is a function. We cannot give like this, because every vertex should get exactly one color. And if you have some age between two vertices, then they should not get same color. They should get different color. Like if they have age 1,2, then if they have age, let's assume if they have age, then they should not get same color. This should not happen. They should get different colors. So what is the answer for this question? Which statement is true? Which statement is true? Three statements are given to you. Every tree admits a vertex coloring using two colors. Remember, this question is not talking about chromatic number. The question is talking about basically vertex coloring, K colorable. This is the definition of K colorable. This is not the definition of chromatic number. This is the definition of K colorable. So remember, this is the definition of K colorable. Definition of K colorable as a function. As a function. Okay. So definition of K colorable as a function. And what is K? The size here. This is the size K. This is your size K. Means this has size K. Number of colors is basically K. How many colors you have? Total K colors you have. Then we will call it, this is K colorable. So then this will be called K colorable. Then we can say this F is K colorable. This F will be called K colorable because this is your coloring function. So this is the definition of colorable. This is not the definition of chromatic number. So tell me, can I say every tree is two colorable? Can I say every tree is two colorable? A tree is a bipartite graph. Why tree is a bipartite graph? What is the reason? Why tree is a bipartite graph? Tree is a bipartite graph because there is no odd cycle. There is no cycle. There is no cycle, so there is no odd cycle. So yes, this is correct. What about this? Every cycle admits a vertex coloring of using two colors? No. Okay, what about this? If every vertex has degree at most K, at most D, then G admits a coloring of D plus 1 colors, D plus 1 colorable. This is correct. This is also correct. So the answer will be what? That will be 1,3. Okay. So this is your all the questions we have seen. All the questions, every TIFR, every gate question we have seen. I did not leave anything. Every question we have taken. So in this class, in this video, you have every question of gate exam, every question of TIFR exam on coloring. Did you understand? Did you understand all the concepts? And did you see the relationship? Did you understand the relationship? So these are the conclusions that we have seen. That chromatic number is basically greater than equal to click number, then that is click number, and that is less than equal to the maximum degree plus 1. This we have seen, the first thing that we have seen. Okay. And the second, can anyone tell me here who understood everything? Like if I want to take your Viva, will you give? Like if I ask you, do you remember why this happens? Do you remember why this happens? Will you be able to answer? Like for example, why this happens? Why this happens? Because this is a complete subgraph, so it should get different colors. It should get different colors. Why this happens? Why this happens? Because of greedy algorithm. Why this happens? Because of greedy algorithm. In worst case, you have to use from 1 to delta plus 1. Only these colors you have to use. Okay. And the next thing, so this is what we have seen. And the next thing, chromatic number. And the next thing we have seen is, what was the next thing? Yeah, minimum number of edges that will be greater than equal to chromatic number C2. Okay. The same thing I can write like this. The minimum number of edges will be chromatic number into chromatic number minus 1 divided by 2. And the another thing is alpha. This is greater than equal to n divided by chromatic number. What is this? Anyone want to tell me what is this? This is the average size of color class. This is the average size of color class. And every color class is what? Every color class is an independent set. Every color class is an independent set. So the independence number should be greater than equal to this. Okay, so these are all the facts that we have seen. And that's it. So this is your coloring chapter, and this is enough for today. We will study this age coloring. We will study tomorrow. In the next class, we will study this age coloring. Okay. So this is clear. Actually, in graph theory, if you notice, we are going slowly, right? In the morning classes, we are going slowly. Like in one morning class, we only study one topic. But that one topic we study in with all the gate, we are taking all the gate questions. Okay, we are taking all the variations and everything we are seeing. Okay, so these concepts are very important because graph theory is very important for gate exam. For any exam, graph theory is important for your interview. By chance, if you prepare very nicely and let's assume you get 600, 500 rank, then in the interview, they will ask you graph theory. Okay, so that is the reason we are learning this graph theory is in a very nice manner. Okay, so in this class, we have seen a lot of questions, all the gate question, all the TIFR question, all the theorems, all the proof, every definition, every concept, every variation, every corner case we have covered. This is the complete package for coloring, vertex coloring. This is the complete package. Okay. Hello, Nikhil. Hello, Nikhil. Nikhil, you are not audible. Hello, Nikhil. Hello, Arpan.
Yes, sir. Am I audible?
Yes.
So I had a small doubt in that star graph diagram. Can you just draw that once? I needed to check one concept.
This is the star graph.
Yes, sir. So when we are calculating the minimum coloring, so when we are, for example, in the central vertex, we start with 1, and then in the side vertex, in the nearest adjacent vertex, we take it as 2. And then in other vertex, why can't we take it as 2, sir? Because like it is not adjacent, the other vertex, the outer side.
Of course we can take 2. Of course we can take star graph is a star graph. Star graph is a K1n. This is a bipartite graph. So for star graph,
Yes.
chromatic number is always 2.
Yes, sir. In one diagram, in the previous example, we did like 1, 2, 3, 4, 5, like in that arrangement. So why can't we do
That
that?
was not for star graph. That was not for star graph. This was this theorem. That was not star graph. I did not take star graph. This was the theorem that if you have a graph G, then the chromatic number will be less than equal to maximum degree plus 1. Okay, this is the theorem. And the graph can be anything. The graph can be anything, any graph, any. Okay, need not star graph. Every graph. Okay, let me take every. For every graph, this will happen. That chromatic number will be less than equal to delta plus 1. And the proof is like this. The proof is like this, that you consider any vertex. Take any vertex you take. Okay, the maximum degree is D. Okay, the maximum degree. Any graph you have in which the maximum degree, let's assume the maximum degree is D or delta, maximum degree is delta. So if you take any vertex you take, then this vertex, see, there can be other, like there can be edges. I don't care. I'm only focusing on this vertex. So let's assume that this vertex has degree delta. Degree delta means how many neighbors are there? How many neighbors are there? If degree delta, if A has degree delta, let's assume A has degree delta. Assume A has degree delta, then how many neighbors are there for A?
N minus 1.
Arey yaar, if degree of A is delta,
Oh, okay. Yes.
then how many neighbors are there?
Delta plus 1.
Arey, what is the definition of degree, Arpan? What is the definition of degree?
So
What is the
basically,
degree of vertex?
what's your vertex is incident to that particular vertex.
So if a degree is 2, then how many vertices are adjacent to you?
2 vertices.
So if degree of A is delta, then how many vertices are neighbors of A?
Delta.
Yes, delta. So there are delta vertices which are neighbors of A. Focus on A. Okay, remember that there can be remaining edges. I don't care. The graph can be very big. I don't care. The graph can be very big. The graph can have any number of edges. I don't care. The graph can be very big. Just focus on vertex A. The graph can be like this. The graph can be big. There can be graph, like graph is like this. The graph is very big. The graph can have like this, like this. The graph can have anything it wants. The graph can be like this. I don't care. Just focus on this vertex A. Now, for this vertex A, I am saying that, for this vertex A, I am saying that if you see, then this vertex will definitely get color. This vertex will definitely get color between 1 to delta plus 1. 1 to delta plus 1. Why? Just think about it. If all its neighbors have, let's assume this has, let's assume in the worst case, what can happen? In worst case, this can happen. In worst case, this can happen that this has color 1, this has color 2, this has color 3, this has color 4, and so on. This has color delta. In worst case, this can happen. In worst case, all your neighbors will have different colors. Just think about it. If all your neighbors have different colors, then those colors you cannot use because your neighbors have those colors. So if all your neighbors have different colors, you cannot use those colors. So in worst case, which color you will use?
Exactly. So in worst case, like we'll till delta it will go, and delta plus 1 for the A vertex.
Yes.
Exactly.
So in worst case, for every vertex, you take any vertex, every vertex will definitely get a color. Every vertex will definitely get a color between 1 to delta plus 1. So this is the idea that your,
Exactly.
so okay, so this is the proof that the chromatic number will be less than equal to delta plus 1. This is not a star graph. The graph is very big. The graph can be anything. The graph can be anything. And okay, the graph can be like this. The graph can be like this. Okay.
Exactly.
Is this
Exactly.
clear?
Yes, sir. Now it is clear.
For star graph, the chromatic number will be 2 because your
Exactly.
star graph is okay as long as n is greater than equal to 1. As long as your n is greater than equal to 1, okay, then your star graph will have chromatic number 2 because star graph is a bipartite graph. That is a complete bipartite graph K1n.
Exactly.
Any other doubt?
No, sir. Now it is clear. Thank you very much.
Hello, Nikhil?
Sir, am I audible?
Yes.
Good morning, sir.
Yes, good morning.
Sir, I have a couple of doubts. First is regarding the independent set kind of thing that we have discussed today. Sir, like I have a doubt, like in a graph given graph, let's say I started making independent set. First block as an independent set, then the remaining vertices I create another independent set, and then can I say like the size of those independent sets will equal to the chromatic number?
No, we cannot say that. Okay, so what you are saying is you are creating independent set. Basically, this type of theorem you are giving that alpha is equal to zeta. Sorry, no. Basically, you are saying that what you will do, you will create independent sets.
Yes,
Okay.
sir. Yes,
So
sir.
see, if you can create, let us assume this is your vertex set, and this you can divide. Let's assume this you can partition into 4 independent sets.
Yes, sir.
You are partitioning it into 4 independent sets. Means
Yes,
some
sir.
vertices are here, some vertices here, some vertices here, some vertices here.
Yes, sir.
Okay, if you can do this, there are 4 independent set. This is the independent set, and so on. And let us assume that this is a partition. Means no vertex can repeat. Like it cannot happen.
Yes, sir. Yes, sir.
Okay, so if you have a partition into independent sets, then you can guarantee one thing. What you can guarantee? You can guarantee that zeta will definitely be less than equal to these. If you have, for example, 4, then zeta will definitely be less than equal to 4. Because what you can
Okay.
do, very simple, you can give red color to this, blue color to this, black color to this, green color to this. So I can definitely say zeta will be definitely less than equal to 4, less than equal to 4. Actually, what you are saying, that is very nice. So this is the logic. But see, what you are saying, like number of independent set,
Yes, sir.
there is no parameter for that. For that, we don't have a parameter. We have parameter for size of independent set.
Size of
Size of
set.
independent set, a particular independent set, largest independent set.
Okay, so I was just like having a graph with the n nodes. So first I just take like उसमें से सबसे बड़ा independent set बना लिया. then
Right,
उसमें
I
से
got your point. This type of questions, the question that you are asking, this
yes
type
sir.
of questions are for, like, okay, once you go to once you go to IIT MTech, okay, then this type of questions will be in your midterm exams. Okay, this type of questions will be in your exams. Like, they will tell you that consider this algorithm or consider this experiment, that we have a graph. In that graph, find the largest independent set.
Yes
Then
sir.
from the remaining graph, again find the largest independent set.
Yes sir.
From
Yes
the
sir. Yes
remaining
sir.
graph, again find the largest independent set. Do like this, keep doing like this. Then finally they will ask you, prove that number of independent sets that
Yes
you
sir.
got, number
Yes
of
sir.
independent sets that you got, that is equal to zeta or not. Okay, so these things are very complicated. Okay, so these things you will study in your MTech. And uh, particularly what I want to say, that there is no parameter, there is no symbol or parameter for number of independent set.
Yes sir.
Are you getting this point?
Yes sir. Got it sir.
See, a particular independent set we have, largest independent set we have, like what is the largest independent set you can create? But how many independent set you can create? Like number of independent set where each one is maximal.
Yes
This is
sir.
this is your point, where
Yes
each
sir.
each independent set is maximal. Okay,
Yes sir.
so that this type of parameters we don't have. Of course, there can be some research. If you want to do the research, then you can find some research papers. You can find in the books, you will not find it. These things are for research papers. Okay,
Okay sir. Got it.
these type of questions you will only find in the research paper.
Yeah sir. And sir, the second question was like if G has a chromatic number and then then we can say that H is greater than equal to MC2. So like
No,
can
the edges are greater than equal to zeta c2,
zeta C2 chromatic number equal to M.
because
Yeah.
between every, if you have minimum coloring, you have done minimum coloring, you have done.
Yes sir.
After doing the minimum coloring, between every color classes, at least one edge must be there. Because if there is no edge, you will merge them.
Yeah. Yes
If
sir.
there is no edge, yeah.
Yes sir. Sir, I got it now. I was just comparing it with the complete graph Kn, and then I thought of like Kn have the chromatic number N. So
No, 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 no,
indirectly,
no, 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 not like that. Because if, yeah, number of edges that will be greater than or equal to
yes sir.
zeta c2.
Zeta C2.
Hmm.
Got it sir.
For complete graph, you can apply this. For
Yes sir.
complete graph, zeta will be n.
Yes sir.
So number of edges will be
For
greater than
complete
equal to
graph,
nc.
the vertex will act as an like that coloring node, like the independent set of a node that we have discussed today. मतलब
I did
complete
not get.
graph का एक नोड जो होगा वो एक कलर के बराबर होगा.
हाँ, complete graph में.
Yes sir. Complete graph का एक नोड जो होगा वो एक कलर के बराबर होगा.
Yes, because in a
Then we can
complete
say
graph, we cannot reuse the color, because that is
yes
a
sir.
complete graph.
Yes
So
sir.
if you give same color to two vertices, then they are adjacent. So there is a
Yes
problem.
sir.
So you cannot reuse the color. So for complete graph, you have to give separate colors to every vertex. So
Every
there will
vertex.
be n colors you need. Okay, and this theorem that we have, that number of edges that will be greater than equal to zeta c2. And
Yes
if you
sir.
notice, for complete graph, for Kn, zeta will be n. So
And
actually this is correct. Number of edges in Kn, that is greater than equal to nc2.
yes sir.
Actually we know this will become equal for Kn. For
Yes
Kn,
sir.
this will become equal for Kn, nc2. For Kn, this is the actually this will become equal, right?
Yes sir. Equal to NC2.
But the point is, this is consistent. But the point is, this result is working, because this will work for every graph.
हाँ ठीक है.
This will
But
work
the
for
reverse way is
every
not
graph.
true, right?
Huh?
Reverse way is not true, right?
What
If
is reverse?
if the graph contains zeta C2 edges, will it be having like M chromatic number or not?
Basically, actually, you should not say. Then in that case, you should not say zeta. You should say that if number of edges is greater than equal to some number kc2.
Yes sir.
This is what you are saying. That if number of edges is greater than equal to kc2, then chromatic number is
Need not
equal
be
to
equal to
k.
K.
Something like this you are saying.
Yes sir.
Something like this.
Yes sir.
Okay. So I think this is wrong, and I think you can easily create a counter example for this.
Yes, sir. Reverse way is not around because KC2, I need a complete graph. Only then I can have only the M chromatic
No,
number.
no, no, no. This is KC2. KC2 means K can be some number.
Yeah,
K can be some number.
yes, sir.
This
So
need not be a this need not be a
coloring
complete
number.
graph. Can you give me counter example? Can you give me a graph? Give me a graph in which number of edges is greater than equal to KC2, but the chromatic number is not equal to K. This
Uh,
statement is, I think this statement is false. Okay, but can we create a counter example? For example, let me take K equal to 3. So 3C2. 3C2 means how many?
Sir,
3C2.
we can do it with the contradiction.
So yeah, what is the contradiction?
Sir, like for having a chromatic number K, we
Mhm.
need a complete graph of KC. We need a complete graph of Kn.
No, 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 no.
Sir,
You are
KC2 to
confusing again. You are confusing again. See, please don't confuse between complete graph and this zeta C2. Please don't
okay.
confuse. Every graph, you take any graph, this A, B, C, D, you take this graph. In this graph, what is the chromatic number? The chromatic number is 2.
2.
And the number of edges, that will be greater than equal to 2C2. Okay. So
Okay.
this is what this theorem is saying. This theorem does not give you much useful information. This
Yes,
theorem
sir.
is saying that if your for this graph zeta is 2, and this theorem is saying that number of edges will be greater than equal to 2C2. So according to this theorem, the number of edges will be greater than equal to 1. Don't confuse between complete graph and zeta C2. For every graph, what will happen? For every graph, G, this will happen. Whatever graph, please notice this. For every graph G, okay, with zeta chromatic number, what will happen? Number of edges will be greater than equal to zeta C2.
Yes, sir.
Okay, so don't confuse between complete graph and all these things. From where
Okay, sir.
complete graph is coming? Like this theorem, in this theorem, from where the complete graph is coming? Don't apply, do that. Okay, so you can have any graph which has chromatic number zeta, like this graph has chromatic number 2, then this theorem says that the number of edges will be greater than equal to zeta C2. So this theorem is saying that number of edges in this graph will be at least 1. That is correct. In this graph, the number of edges is at least 1. But actually, how many edges are there? There are 4 edges.
Yes, sir.
Okay. So
Useful
similarly, actually, you can notice that this is the question that I am saying, that if your number of edges is greater than equal to KC2 for some K, or maybe T, you can take maybe, because you are confusing between, okay, don't think about complete graph. Please don't think about complete graph.
Okay, sir.
Then, okay, so for example, if your number of, let me take, for example, let me take T equal to 3. It means your number of edges is how much? Your number of
3.
edges is 3C2.
Yes, sir. Greater than equal
Your
to
number
3.
of edges is greater than equal to 3C2, or 3C2 is means 3C2 is basically 3. So your number of edges is greater than equal to 3, but still you can create chromatic number equal to, still you can create chromatic number, you can create anything. See, you can create chromatic number 2. How can you create? You can take this graph.
Path graph. Yes, sir. Yes, sir.
Okay, so
Cycle
you can
wise
take this
diagram.
graph, you will get chromatic number 3, and you can create chromatic number 4 also. You can create. How will you create chromatic number 4? Because number of edges is greater than equal
At
to 3.
least 3. Yes, sir. So I can take
So
more edges
so
and
you can
then
take
create
K4.
4.
You
Yes, sir.
can, now
K4.
you can take your K4. So this statement is definitely false. This statement does not, okay, this statement is definitely false. If your number of edges is greater than equal to TC2 for some T, then chromatic number will be T. This statement is false.
Yes, sir.
Chromatic number can be anything. You can create chromatic number equal to, you can chromatic number equal to 10
And
also
10.
you can create. You
Yes,
can
sir.
take
K10.
K10.
Yes, sir. Yes,
Okay.
sir. Got it, sir.
So don't confuse between chromatic, this theorem and the complete graph.
Complete
Okay.
graph. Yes, sir. Got it.
Any other doubt?
No, sir. Got it. All clear. Thank you.
Anyone has any other doubt? Okay. Thank you, everyone. See you tomorrow. So no, in the digital logic class. Okay. In the evening, we have digital logic class.